We are live.
Yay! Welcome to the stream, YouTubers. Take two. All right. 20 people are here. I'll just wait for a couple more to show up. So Kaya, the title of your talk is slightly different than it was earlier, right?
Yeah, I think in the beginning of the summer, we had a very broad general title.
Okay. All right. Yeah, I think we just took that off your project journal or something. So, all right. So I won't announce your title exactly.
Yeah, the same thing happened with mine. Like we found something really interesting and then we changed like midway through. So
Yeah. No, that's
the
way real work.
The titles on the schedule, I think, are up to date. So if you want to read them up there on the online schedule.
Well, that's what I was looking at. So on the web page, I had to refresh the page. There we go.
Ta-da!
Claire is a wizard. If you don't learn anything else this summer, hopefully that's what you learned. Claire is a wizard.
Mm-hmm.
I had the YouTube live stream. I had the YouTube live stream up and everyone was like talking over each other and I was like, what's happening?
Shall we get started then?
Yep. Okay. Welcome everyone to the 2020 REU Student Symposium. We have a full day of talks today and tomorrow, and then the poster session will be tomorrow. So the first speaker this morning is Kaya Wall from the University of Colorado, who will tell us about deep space radiation genomics. Right? You ready?
Share my screen. Sorry. Oh, there it is. Okay. My name is Kaya Wall. I'm a rising senior at the University of Colorado Boulder. I am a creative design and technology major. My mentor is Dolores Nip, and my graduate student mentor is Valerie Bernstein. And we are working on a deep space radiation genomics experiment and looking at the effect of the magnetotail and the bow shock. Here's a little background on what the DSRG experiment is. A team of researchers from various universities is sending an experiment on Artemis 1 mission that will be flown past the Van Allen belts towards the moon. The experiment will expose a collection of yeast to a space radiation environment. The team will analyze the effect of microgravity and space radiation in genes. The yeast culture needs to grow for 3 days outside of the magnetotail to ensure the radiation environment is not altered by particles trapped in the magnetotail. My specific goal for the RU research was to create a yes-no table for when the DSRG experiment can or cannot start. To do this, we had to calculate the moon's position over a 3-year period and compare the moon's position to the magnetotail and bow shock. We also wanted to determine if passage through the bow shock could alter the radiation encountered by the yeast, and to find examples of extreme conditions that could be encountered during the experiment. Background. Solar wind deforms the Earth's magnetic field into a structure called the magnetosphere. And in this magnetosphere, there's the magnetotail. That is this structure here in the yellow. The magnetotail acts as a barrier to energy particles. The moon spends about 6 days of its lunar cycle in the magnetotail. The bow shock is a structure that forms around the magnetosphere that slows down solar wind. The interplanetary magnetic field is then compressed, which produces a field gradient that can deflect low energy particles. The figure to the right shows the moon's orbit compared to the position of the magnetotail and bow shock. This figure shows our general goal for our research. To calculate the moon's position, we use Python. There is an astronomy library called PyIthon. This library can calculate the moon's position in right ascension and declination. It can also calculate the moon phase and the distance from the Earth to the moon. We needed to calculate the moon's position in equatorial coordinates, GEI, that's right ascension and declination, and then convert them to ecliptic coordinates, GSE, because the magnetotail lies on an ecliptic plane, and we needed a plane that would be centered around the Earth. To do this conversion, we used an outline from Hapgood 1992. In equation 4, here, you can see a transformation matrix, P. It transforms equatorial XYZ Cartesian vectors to ecliptic XYZ Cartesian vectors. P is defined as a matrix multiplication of 2 rotation matrices. The first was the rotation from the Earth's equator to the ecliptic plane, the Z-axis, and the next was the ecliptic plane to the first point of Aries, or the direction of the sun, that's the x-axis. Here's an illustration that can help you visualize the coordinate system that we were working with. Right ascension and declination are the latitude and longitude angles. It's right ascension, this is declination, relative to the equator and equatorial coordinates. And GSE coordinates are defined as the positive x direction is pointed from the Earth to the sun, the positive y direction is pointed towards dusk, and the positive z direction is the northward direction out of the ecliptic plane. The vernal equinox is the first point of Aries, which points in the z direction of the ecliptic plane. We were able to define the magnetotail's position in GSE coordinates by using another resource provided by Hapgood. We were able to define its position at -60 Earth radii in the x position. The magnetotail has an offset in the y direction that is defined by delta y. That equals the moon's position in the x direction times 29 over solar wind velocity, which was found to be about 400 kilometers per second. And the magnetotail has a radius of 30 Earth radii. And we found that the bow shock is centered around the magnetotail with a radius of 50 Earth radii. The results from our calculation of the moon's position and position of the magnetotail are shown in the 3D graphs below. It shows the position of the moon, which we collected data for every hour for a 3-year launch window. And in the center, we can see the Earth at 0, 0, 0. That's the center. And the ring around it are the moon's positions. 2 large circles in the YZ view represent the magnetotail and bow shock. That would be these 2 large circles here. Though the magnetotail is shaped like a bullet, for our purposes, we use circle where the moon's orbit and magnetotail intersect, because that's the only region that we were really interested in. So on the graph, the red represents the moon's position when it's inside the magnetotail. And here you can also see that the offset the magnetotail has. Here, the magnetotail is centered at -60, 0, 0. In reality, there is an offset in the positive y direction that's defined by delta y. The yellow positions represent when the moon is in the bow shock. And this purple area here represents a 3-day window that the experiment needs to have before it can start. That way it doesn't run into the bow shock. Here we see graphs that show a comparison of when the moon is in the magnetotail and bow shock versus when there is a full moon. Before we had finished the conversions from equatorial to ecliptic coordinates, we used the knowledge that during a full moon, The moon is in the magnetotail for about 6 days to get a sense of which dates would be in the yes and no table. The moon enters the magnetotail 3 days before full moon and takes about 6 days to pass through. And that you can see from here. This graph shows that on a full moon, when the surface of when the percent of the surface is illuminated here, it's at 100, the moon is in the magnetotail. So it lines up with every full moon for this 3-year window that is in the magnetotail. This was promising to see because both methods we used to create a table lined up perfectly together, ensuring we had the correct data. The above graph shows the entire time span that the DSRG experiment can take place, and the below graph shows a month of data. So you can clearly see when the moon enters and exits the bow shock in the magnetotail. Another consideration we wanted to take into account was the effect the bow shock would have on the experiment. When my mentor and I were first contacted about the experiment, we were only asked to compare the moon's position with the magnetotail. After researching the bow shock, we found that medium energy solar wind ions can be accelerated and or reflected by the bow shock, and that particles with high energy, such as galactic cosmic rays, can be deviated by the bow shock, but are not blocked. Overall, we found that particles relevant to the experiment will not be affected by the bow shock, but still chose to create an additional table that includes a limitation of the bow shock. It was important for us to look at extreme examples of what could happen to the magnetosphere that would negatively impact the results in the experiment. One scenario we found was in May of 1999, NASA's ACE and WIND spacecraft each observed that the density of the solar wind dropped by more than 98%. Earth's magnetosphere swelled to 5 times its normal size. And several interplanetary spacecraft observed the most distant bow shock ever recorded by satellites. An event like this has not happened since. Though it is impossible to predict extreme space weather events, we thought it would be important to inform the team about a worst case scenario. And here you can see a graphic of this. I'm going to play it a couple times. So at first we see a normal bow shock and then encountering this low density area and expanding. And just so you can get a good sense of what actually happened and how unusual this is, to say the least. Another extreme example that shows how the magnetosphere can be altered can be explained by examining a sequence from the simulation performed by Shing in 2020. This shows that the magnetosphere shows magnetospheric deformation during the passage of an interplanetary shock in the solar wind. The black dot, that would be here, represents the moon. The color bar shows number density of ions in log scale. The shock first compresses the Earth's bow shock here, and then starts to deform the magnetotail. That's here. And then severely deforms the magnetotail for a short amount of time, leaving the moon in an unusual shock magnetotail environment. The sequence of events occurs only a few tens of minutes, but the effects in terms of magnetotail disturbance may linger for more than a few hours. The results from the graphical representation of the moon's position compared to the position of the magnetotail and bow shock illustrated that there were 9 to 12 days each month when the experiment did not start. 2 decision tables were created, one providing yes or no decisions considering only the magnetotail and another considering only the bow shock and the magnetotail. Both tables exclude an additional 3 days to ensure that the experiment can run for a full 3 days before it enters the magnetotail. Experiment must go beyond the Van Allen belts using an outside bow shock limitation. Only 17 days of each lunar cycle is available for data collection. And if an outside the magnetotail limitation is used, then 20 days out of each lunar cycle is available for data collection. After researching the bow shock and the effect it may have on the radiation environment, it is believed having a DSRG experiment run while passing into the bow shock will not have a significant impact on the experiment, and extreme events that would severely alter the magnetosphere shape occur about once a decade from an interval of 24 to 72 hours. but predicting such events is currently beyond forecasting capabilities. And that's the end.
Very nice. It helps if I unmute. Hi. Are there questions?
I've posted a question into the chat for you, Marty.
Okay.
From YouTube.
Yes. So what is the inclination of the moon's orbit relative to the ecliptic? And does this affect the results?
That I actually don't know the answer to. Maybe I have all my mentors here if they know the answer.
Yeah. I'm sure that's included in the ephemeris.
Right. Yeah, that's why she did all of the rotations, so that we would know how the moon's position was with respect to the Earth, with respect to the solar wind, with respect to the ecliptic and the celestial equator.
Right. I'm trying to remember the inclination of the moon. It seems like it's only about 5 degrees. Is that sound reasonable?
5 to 7. 5 to 7.
Yeah. Other questions? So I have one that so is there like a radiation sensor as part of the payload that measures how much dose the yeast is getting?
I actually don't know. I'm not very involved in what the actual payload is doing.
If I may, yeah, the answer is yes. We're going to have both passive and active radiation dosimeters.
Okay.
We have a timer to know when did the yeast growth begin and when did it end, so that we can compare the results from what we're measuring with the radiation doses types.
All right. Awesome job. I guess I have to turn on my video so you can see me clapping.
I think Yun Chen was going to explain the evaluation, I think, right just before we move on.
Okay.
Oh, so I post, and also Kennedy post again the evaluation form for all the students. And when you go to the form, you can choose one of the presenter today, and then you can write down the rate, and some comments will be very helpful for the student. We will give the feedback to them after the talk. So all the mentors and the students' evaluation for the presenters are very welcome. Okay.
All right. Thanks. We don't want to get too far ahead of schedule in case people are popping in to see specific people. So we'll pause for just a minute. Everyone can get another iced coffee. And Kennedy, you all psyched and ready?
Oh yeah. I'll just prepare as we prepare. Got my little dancing son. He's back.
All right.
He's excited. What did I say last time? I said he's listening to the music of the stars.
All right.
Can you see my laser pointer?
Yes, we can.
Excellent. How do I hide the little videos, do you guys think?
Hide them?
Yeah, they're in the way. Oh, maybe I can. Oh, okay, they're gone.
Oh, you mean the Zoom videos? Yeah, you can just minimize that.
Yeah, all righty.
But don't get tempted to exit from Zoom.
I know. It's kind of abandoned ship here.
Mm-hmm. All right. Let me get my timer reset. Okay. I think we're probably ready to start. Okay. Our next speaker, Kennedy Farrell from Texas State University, will tell us about solar activity above and below the solar surface.
Hello,
Thanks.
so I'm Kennedy Farrell. My project title is Investigating Activity Below and Above the Solar Surface, as Marty says. So let's just jump right into it. We've got a little dancing sun and he's ready to see what we're working on. So the solar cycle is a period averaging about 11 years, and it's distinguished by magnetic activity of the sun and how that activity changes over time. There are many activity indices observable above the surface, and here I've actually shown the activity of sunspot number, radial flux, and then MG2 index. So those are 3 examples of the activity that can be observed above the surface. And a couple of things to note about these plots is that it seems the minima as we go forward in time are getting deeper possibly. So that's maybe something interesting and one of the research questions that I'll be looking into. As well, it seems they're getting wider over time. And in general, there does seem to be a trend overall of decreasing activity. So these peaks are actually getting lower as we go on. And specifically, I'm interested in these solar minima periods. So whatever's happening there and why they might be becoming deeper or wider is of interest. So why is solar minimum interesting right now? And those are a few of the reasons. So accompanying the overall trend of decreasing solar activity, I can see how this might relate to spotless days on the disk. Here, I've plotted the percentage of spotless days each year. So that just means a day that there are no sunspots on the disk. And this plot shows again that activity over time seems to be going down. And you can see that by the increase in spotless days. So days that there is no activity on the disk. As well, we can see that previously minimum has just been defined as a singular point. And remember, this is per year. So this suggests that the minimum is only spanning 1 year or 1 point. And as we go on, we see maybe a bar, so 2 points, and we're not sure quite yet for this current minimum as we're still experiencing it. So this suggests that the minima are getting wider, possibly deeper. My research will investigate that. So why is this happening and what is happening to solar minimum? My research team is interested in evaluating how the minimum above the surface correlates to minimum within the sun's inner layers. My overall research goal and research interest is in identifying and comparing solar minimum above the surface and below the surface. So below the surface, there are no direct methods for measuring magnetic activity. So we can employ a method called helioseismology, which I'll describe in detail soon. But first, I'll explain that the 3 activity indices that I'm using for above the surface, sunspot number, radial flux, and MG2, and where they are located. Here we have this lovely image. So go to the photosphere here. Right here in this green layer is where the sunspots appear and where they can be observed in the photosphere. Following that, MG2 index appears in the chromosphere. And following that, the radial flux can be observed from the inner corona. For the frequencies, I'll be using data from GONG, the Global Oscillation Network Group. And this data is continuous from around May of 1995 to the present. So that is the time frame that I'll use to evaluate minimum above and below the surface. If you can hear my cat, he's meowing, he's excited. And this is really interesting in identifying what kind of data I have for the layers beneath the surface, because the magnetic field is believed to be generated in this layer here, not labeled, at the base of the convection zone. And so identifying where I'm able to evaluate internally of the sun, I'll be able to maybe see where minimum is there. my data set allows me to evaluate minimum between cycles 22 and 23, 23 and 24, and the current minimum between cycles 24 and 25. So understanding solar minimum above the surface, because of my data set and the frequencies that are derived from GONG data, I have averaged the surface activity based off a 36-day period. It's a GONG month, so that's just the monthly period that frequency data is taken. And so to match that data set, I have plotted my 3 surface activity indices here, and you can see that they're actually in phase with each other. And on the right, I have again sunspot number, radial flux, and MG2 index. I'll detail these minima bars later in a table, but we can see a little bit that maybe they were closer here in this previous minimum between cycles 22 and 23. And the green here is the absolute minimum for each data set. And then later on, we see that maybe there is some variation. This one is quite a bit further than these two here. And again, I'll detail the exact epoch of each of those later in a table. So what is helioseismology? Well, it's a study of oscillations created by acoustic waves that travel throughout the solar interior. They penetrate each of the sun's inner layers and travel throughout the sun, creating patterns on the surface. So these can be identified as red and blue shifting regions and oscillations. Each of those patterns is categorized into a mode of oscillation, of which there are millions. So each mode can give me information about layers within the sun. As you can see here in this image, the different waves travel through different regions of the sun. As we go deeper to the core, sound speed actually increases. So depending on which layer I can identify that they're coming from, I'll be able to have more information about certain parts of the sun. So all of these are acoustic waves, and these little dashed lines actually kind of illustrate the boundaries of each wave. And so here we see an upper turning point and a lower turning point. The lower turning point just corresponds to how deep within the solar interior the wave can penetrate. And the upper turning point represents the point near the surface where the wave is actually reflected back inside. Hi, Cat is on the computer. Okay, so all of these are acoustic waves, and you can see they travel to different points in the interior. So identifying these points or boundaries will tell me which modes from the data set that I have carry what information about the interior. And the frequencies that are calculated from each of these modes serve as an activity proxy for the interior, for which there is a known positive correlation detailed in this point here. It's widely documented and studied in helioseismology. And as well, I should note that I'm studying global modes of oscillation, which just means that the mode is oscillating over the entire surface of the sun rather than in one particular area. And that'll be more important here as I discuss how the frequencies are actually calculated. So taking Dopplergrams for each GONG month, these actually can be analyzed into a time series by each L of the 3 quantum numbers, N, L, and M. So this can be created, and then you can take the FFT for each of those and create this M-nu power spectrum by frequency. Each of these little bars and points can actually be taken into this power spectrum, where each peak corresponds to the frequency that I might use later on for each of the modes. So then here, taken from NLM, each of the modes is M average, which gets back to my point about the global modes of oscillation rather than local. So they're averaged over the entire surface, and we're able to find the frequencies and the modes in the data set. So my data is continuous from May of 1995 on. And that gives me 505 overlapping data files. So each file contains around 1,600 modes, and that adds up to over 750,000 lines and different modes to analyze. They're overlapping by a period of 18 days. They're moved by 18 days, which would be half of that gone month. So the modes carry information about different parts of the interior, which is why it's important to map which modes are present in all files. That way I can find, I can map the frequency variation over time with little variation. Here is an example of the modes present in one file. As you can see, there are many. Again, that's around 1,600. And whenever I found the common modes among every file, there were 247, and that is a demonstration here of those. So for my analysis, I'll find common modes among each file here and calculate frequency shift with respect to a reference. Since I'm interested in solar minimum, my reference period is based off of the previous solar minimum around 2008. So now that I'm able to identify which modes are present in every file, I can start to plot the frequencies and the oscillation over time. Here's a sample plot from earlier in my research that I created based off one mode. So this is n equals 8, L equals 93. And again, going back to the correlation between internal frequency and surface activity, this actually has a correlation, a Pearson correlation of 0.92. And here is a broader example using all modes of that correlation. Since I'm interested in what is generally happening over time and the frequencies oscillations over time, I actually use the common modes to calculate the mean frequency shift here, which gets me a much better correlation and a better idea of what's happening within the solar interior. So those are calculated using this lovely formula here. And it accounts for error and also mode inertia. And mode inertia is just the weight and not probability, but the weight that each mode carries to change into another. And I'll also point out that here in the lower frequencies, there is a drop in correlation. So that's just something important to note and maybe interesting about the frequency range that I'll be analyzing. So as we discussed whenever I introduced you to helioseismology, the acoustic waves that travel throughout the solar interior have different boundaries and turning points. So depending on where these turning points are, the waves will carry different information about the layers that they travel through. Using the set of common modes that I had found, these plots can be created that define the upper and lower turning points. So this is upper here, lovely title, and then lower over here. And you can see that for the upper turning point, there are three distinguished sections of a low frequency range, mid frequency range, and high frequency range. And then for the lower turning point, we can use this formula here that actually takes into consideration the sound speed I was speaking of earlier, depending on different depths of the interior. After understanding the turning points of my common modes, I was able to use correlation again between the activity indices. So here we have radial flux, sunspot number, and MG2 index. When plotted against nu by capital L, which is just the square root of L times L plus 1, I was able to see that there is a region here of high correlation, and in general, I was able to see where my modes fall. And again, nu by capital L was an important factor to plot against because it's a known indicator for layers in the interior. When analyzing this more closely, I was able to see that my modes mostly are falling below 70 or 75, which actually indicates that they're oscillating through the convection zone. So that was a big discovery for my research, identifying which region of the solar interior my modes were carrying information from. And going back to the diagram that I showed you of the solar interior and its layers, that's a really important discovery because at the base of the convection zone, is where the magnetic field is believed to be generated in the line. So seeing that there was a high correlation for those modes made sense, and a possible explanation for that could be because it's so close to the source of the magnetic field. So that is there. And then again, below about 75, but modes below 70 will indicate that the modes are in the convection zone. So using those frequency ranges calculated from the upper turning point, I was able to plot each of these. And again, you can see the minima bars for each solar cycle that I'm interested in, which I'll detail later in a table. So again, the upper turning point just represents the point that the wave is reflected back into the solar interior. And I've used an 11-point smoothing window for each of these curves, and that helps me identify minimum. For the lower turning point, I've also plotted each of these regions using 6 sections of the convection zone. For example, this would represent the top 5% of the solar interior. And again, I can identify minimum in each of these. For all of these plots, you can see that they have a very similar shape, kind of going back to how the frequencies are correlated to surface activity. So traveling through the convection zone, I can identify minimum within each section of the convection zone as well as above the surface, which might be helpful to identify how solar minimum is different in the current minimum versus other minima. So this is the table that I've spoken about. Sometimes seeing the graphs is a little hard to compare, especially because there are so many sections that I'm analyzing. But to compare minimum above and below the surface, here I have, let's see, each has the cycle noted, and then these are my surface activity indices. Again, cycle, these are my upper turning points, so the frequency ranges that I spoke about. And then here, the lower turning points, so the plots that I had just shown. So all of these have an uncertainty of plus or minus 18 days because they're averaged over 36-day periods, and each data set is moved by 18 days. The green highlights represent the absolute minimum. So for each data set, this is the deepest minimum. Again, the deepest minimum, right? Which is really interesting because we're seeing that while we might be wondering, are we in the deepest minimum today? Are the minima getting deeper as time goes on? It seems that they're not, because the deepest minimum for many of these activities and the internal frequencies was sensed actually in the previous minimum between cycles 23 and 24. So this leads me to some of the conclusions that I found from my data and my analysis. So the sunspot minimum is later than the minima in radial flux and MG2 index. Going back to this plot, we can see right here, that is in fact true. One explanation could be that we are entering a deeper minima, or that there is, and also that there is not enough data yet to say for the current minima if it will be the deepest or how exactly it is different from the previous minimum. And that is just because we are still experiencing it. So the current minimum between cycles 24 and 25 is not as deep in the minimum during cycles 23 and 24. And that's something that I suspected from the beginning, and you can see from the beginning of the presentation, because it does seem that it may be getting deeper, but we can see the whole way through that it does seem to be getting wider as time goes on, and that reflects back on the spotless days plot percentage per year. So the minimum during cycles 22 to 23 is different layers in the convection zone sense minimum around the same time. And that is also true. So we see the higher layers of the atmosphere, which reflects on the radial flux and MG2 index, actually sense minimum between cycles 22 and 23 around the same time. And again, between cycles 23 and 24. And so that is reflected by these absolute minimum that were all sensed in the previous cycle rather than the current cycle, indicating that it is not as deep as, or is not deeper than the previous cycle. And as well, we can see that different layers of the convection zone had different epochs of minimum, but they are being sensed during the previous cycle. And that, going back to what I said before, there may not be enough data in the current set to identify how the current minimum differs from previous minima. And so before I present at the fall AGU meeting, I'll actually add several months of data to have more conclusive results. Acknowledgements.
All right, very nice.
Thank you.
Good
It's
stuff.
exciting
Good
stuff.
stuff. Yeah.
Any comments?
Yeah. There's a couple of questions in the chat.
Okay.
Nick asks, so the lower limit on your correlations looks like it's about 30. So what depth does that correspond to in the sun?
Here?
Yes.
I assume here. Yeah, so this would just be about, I suppose, maybe halfway through the convection zone. Right here, we're close to the surface. And so this nu by L is taking us further in. And I just had pointed this out because I was excited to see this region where there was such a high correlation. And that indicates to me that there's a region of the convection zone that has sensed an even higher correlation to the activity of the magnetic field. So these are all in the convection zone. Does that answer the question?
Yeah. Okay. So mu over L being small is at the surface, and then as that number gets bigger, it goes deeper and deeper.
Correct.
Okay. Great. Tom Woods says that when you look at solar irradiance, it's that the 2008 minimum was the lowest. I think on the magnesium 2, that is kind of your irradiance proxy. It kind of comes to about the same level every time, but yeah, if you look at other wavelengths, maybe it was slightly deeper.
Mm-hmm. Yeah, I would say that my project supports that.
So, and I had just one final question. So your correlations become smaller and smaller. Are there any times when that correlation is negative, meaning that it's out of phase?
For my results, no. I do know that in a previous project, my mentors had noticed negative correlation. So you may ask them if you're interested in that. But yes, no negative correlation for my data set.
Can I say something here?
Yeah,
certainly.
So when we looked at the minimum between cycle 23 and 24, and we just calculated the correlation only for 2 years, we could see negative correlation at that time. And especially with low degree modes, because activity was still going down in 2008, but for low degree modes, like deeper in the interior, modes had started seeing increase in their frequencies. So that is why actually we could see the correlation at that time.
Okay, so there are two more questions, and then we'll close it. So Tom Woods asked about the dates of the minima. I know earlier you sort of pointed out that they were not necessarily all perfectly aligned. Was that true, that they do not line up?
Yeah. So here we can see. I can also go back to the plot, but I do feel it's easier to see the exact date point that we marked the minima at. So even just looking at that first plot that we had talked about for the above surface activity, there is some variation, but they seem pretty close together here. Maybe sunspot number a bit later compared to these other two. And remember, these are moved by 18 days, so however many points would be in between is definitely less than the actual number of days. Leading to the uncertainty. And then here again, we have in 2009 versus 2008, still only moved by a few data points. And then, yeah, so for here, we have in 2018 and then the end of 2019, you know, so yes. and as we go on, you know, there, some of these right here, amazing. Look, these are all the same. Incredible. So that's for the upper turning point in the cycle between, or the minima between cycle 22 and 23. The overall frequency shift, and then 2 of the frequency bins, we're actually sensing minimum at the exact same point, with an uncertainty of plus or minus 18 days. So that's really interesting. And as we kind of move on, we see that there is more variation.
Okay, all right. And the final question from YouTube that is perhaps a little open-ended and maybe something you hadn't thought of yet. If you think of a larger context where the sun is a star and there are other stars that are similar, do you you probably didn't think of it during the project, but maybe think about it for a second here. So is there correlations with the sizes of stars and so on? Maybe this is a kind of a broad question, but yeah, they say if we think about this research in a larger sense, how can we connect this to other stars of the same size, and what does this suggest for future space research?
I would be maybe uncomfortable saying that we would see exactly the same processes in a star that was not a very similar size and luminosity and all of those things to our sun. I definitely, I don't think I'd say that. But as far as the size, I mean, I think more than anything, it would change the layers of the interior. And so the actual distance the magnetic field is affecting. And so I'm sure it would be comparable, but I think it would depend on more of the initial conditions, the actual star's characteristics.
Okay, that's great.
Yeah.
Okay, let's thank Kennedy again. Good job.
Thank you.
All right, and the link for the evaluations was posted again in the chat, so hopefully everybody can take a moment to do that while Peter is getting his slides queued up.
Great, thank you.
All right, someone in the chat says the PowerPoint looks tasty. I think they're talking about yours, Peter. All right, so our next speaker is Peter Breslin from Trinity College Dublin, who is visiting us at a not too unreasonable time for your time zone, and he's gonna tell us about his tasty work.
Yes, thanks, Marty. So as Marty just said, my name is Peter Breslin. I study at Trinity College in Dublin, and I study astrophysics. I'm going into my final year. And this is the project, Time Analysis of the Source and Thesis Similarity. So first of all, how do we interpret this title, this tasty title? Firstly, we have to introduce source and thesis. The Solar Radiation and Climate Experiment is a spacebound satellite that measures the solar output. And the Total and Spectral Radius Sensor, TSIS, is an instrument on board the International Space Station built for the same purpose. And both source and thesis collect spectral and total solar irradiance measurements. Total solar irradiance, or TSI, is required for establishing Earth's total energy input, while spectral solar irradiance, or SSI, is needed to understand how the atmosphere responds to changes in the sun's output. And both source and thesis have a spectral irradiance monitor, a SIM instrument, which is used to collect the integrated SSI from 200 to 2,400 nanometers. And this is an important range, as this integrated SSI makes up almost 95% of the total solar energy. So now that we know what source and thesis is and why they are similar, What does the time analysis have to do with it? What does that mean in the title? Well, source and thesis had a 2-year overlap in which they gathered measurements at the same time. And this project focuses on the analysis of the data collected from this overlap. So why are we looking at these measurements? Well, the source mission was extended by 12 years. There are many delays to the projects intended to replace the satellite, so it was kept operational to ensure a continuous data record for solar variability was maintained. But naturally, source has degraded substantially as a result. A combination of better technology and lessons learned from the source mission meant that thesis was launched with a higher degree of accuracy. And before the source mission ended in February this year, over 2 years of overlapping measurements were collected. And by comparing these measurements, we can determine a new scaling factor to bring the irradiances measured from source to the absolute calibration for thesis. And this will improve the quality of the solar record source has helped to maintain for the past 17 years. And just a little word about the SIM instrument. So it uses 3 photodiodes to make measurements in the ultraviolet, visible, and infrared regions. And an electrical substitution radiometer is then used for measurements beyond 1600 nanometers. And you'll see the distribution of this spectral range more clearly in the following slide. So the 2-year overlap began in March 2018 and lasted until the last day of the source mission in February this year. So this comprises a total of 700 days, 539 of which contained quality data from both instruments. And for this comparison, the latest source and thesis datasets were used. And those are thesis version 4 and source version 27.8, which is a preliminary source version 27. And these are both level 3 data products, meaning they contain the fully calibrated daily averages. So in the first plot here, we see the irradiance measured from source and thesis SIM for each wavelength averaged over the full overlap period. And as indicated, thesis is the blue curve there and source the red. And what's nice about this plot is even after 17 years of degradation on source, we see how similar both spectra are to one another. And this really demonstrates the effectiveness of the degradation corrections that have been applied to source since its launch. You can see that most of the variation occurs in the ultraviolet to visible range around 200 to 500 nanometers, but it's difficult to see. Looking at the differences between these measurements in the second plot gives a better sense of the overall calibration differences. If the irradiance measured by source and thesis was the same, the curve would lie along the horizontal dotted line at y equals 0. And it should be noted also that the large jump at about 310 nanometers in the bottom plot, that's due to the detector changing from the ultraviolet to the visible. So from the UV to the vis diode. So this plot here shows the fractional standard deviation from the mean irradiances measured from both source SIM and thesis SIM for the overlap period. And we see straight away from the plot on top that thesis has quite a lower standard deviation percent as expected. But it should also be noted that the variability from wavelength to wavelength appears much smaller for source. This is emphasized in the larger noise envelope in thesis around 300 to 400 nanometers, which can be seen more clearly in the bottom plot showing this wavelength range. As an additional spectral alignment still needs to be performed for thesis, this is caused from a residual misalignment between the various days of the thesis spectrum. So that should clear up in the following version. The spike in source at 308 nanometers is an artifact due to the current processing also. And as noted in the plot there, the calibration for that gap is in progress. So image plots allow us to add another dimension to our visual representations of the irradiance throughout the overlap. So the X and Y axes here show the day of overlap and wavelength respectively. And these dimensions are shown on a linear scale with the days not included in the overlap period, i.e. the unmatching days or the unusable scans. Those are highlighted as the horizontal strips of one color spanning the X range. The plot on top shows the irradiances measured from both instruments throughout the overlap, represented as a color intensity in the Z dimension. And this gives us a clear view of the spectra on a day-to-day basis. Once again, we see that the measurements between both instruments are extremely similar. And if they were, for instance, if they were different, then this could indicate that the instruments were not recording the data correctly or as intended. But we can see the overall calibration differences better in the second plot below, showing the ratio of the two irradiances here. And it can be seen that the irradiance ratios all fall within 10% of each other. And this view also gives us a better sense of the overall calibration differences, as well as the variability for each overlap day. For instance, if we see that a particular wavelength shows a lot of variability at a given time, then this provides a good indication that it is probably an instrument artifact that took place at that time. So as an example, the two black circles there are highlighting something like this. We could then identify the time period that these artifacts occurred at by looking at the y-axis, and then determine if the fault was due to source and thesis or thesis. So in the plot on top here, we see the standard deviations from the 28-day average irradiances measured from both source and thesis sim for the overlap. And it's beneficial to take a moving average of 28 days, as this corresponds to the length of about one solar rotation. So therefore, it gives us a better idea of the long-term trends of variability. So yeah, we see the standard deviation is a lot lower for thesis compared to source. In this way, we can also clearly see where each instrument switches from one detector to another. So for instance, on the source plot, at around 310 nanometers here, we see the change from the UV to the vis diode, from the vis to the IR diode at 950, and the IR to the ESR at 1600. And this is indicative of the different signal to noise ratios on each of the detectors. So this also gives us a nice representation of the detector performances. For instance, at the low irradiance levels of the vis and source, the signal to noise is not very good. There's a pretty sharp increase in the brightness of the sun after around 400 nanometers. So the signal to noise increases, which reduces standard deviation. And the vis diode and source doesn't handle this too well when compared to thesis. And one thing to note also is the high standard deviation in source, about 400 to 450 nanometers here. This is not seen in thesis. So we can determine from that it's an instrumental artifact on source's part. The image below shows the ratio of the standard scores from source and thesis for the overlap. And standard scores or Z scores represent the number of standard deviations by which the ratio is above or below the mean value. And a positive Z score would indicate the ratio is above the mean value, while a negative Z score indicates the ratio is below the mean value. And particularly high Z score ratio values at certain time periods are indicative of instrumental effects during those times. So due to large uncertainties associated with the ESR range in the source sim instrument, we see a lot more variability in the Z-score ratios for this wavelength range. And these uncertainties in source are due to temperature instabilities within this wavelength range. So when determining the scaling factor to bring the source sim radiances to the thesis sim absolute calibration, naturally we want to use the best or most stable data available. And we can do this by looking at the measurements taken during periods of low solar activity. But firstly, we need to define a quiet zone period. So we did that. We compared various solar proxies and chose a time range based on the activity from the proxy ensemble, which is shown in the plot here. Each curve represents a different proxy here. So each proxy has been fitted to the same scale for ease of comparison. And the shaded region between the dashed pink lines indicates the period we settled on. And 52 out of the 62 days contained within that region had quality data from both instruments. So the atmospheric laboratory for applications in science, or ATLAS satellites, were NASA missions for the study of the atmospheric variations due to the solar changes over the solar cycle. And SOURCE-SIM is using the absolute calibration from the Atlas III reference spectra. And this calibration was made to SOURCE post-launch, whereas TESIS was ground calibrated to a higher degree of accuracy. So in this plot, we compared the different calibrations made to SOURCE. The blue curve shows the ratio between the Atlas III calibrated SOURCE radiances and the radiances measured from TESIS. And this represents our current SOURCE and TESIS data. The green curve shows the same ratio of TESIS, but using the uncalibrated SOURCE radiances. And this represents the SOURCE data without an absolute flux calibration. And the horizontal dashed line represents the TESIS measurement. So if the SOURCE values were perfectly aligned with TESIS, then this curve would be the curve would be along that straight line. And also plotted in the pink curve there is the SOURCE TESIS ratio for our newly defined quiet sun period. And so that represents our new scaling factor. So if we firstly look at the Atlas III calibrated SOURCE, we see that the radiance differences in the visible region are around 1% away from the TESIS measurement, while it's about plus or minus 7% at around 300 nanometers in the ultraviolet. And moreover, the differences are 6% higher in the infrared than the TESIS measurement. And also in the IR, we see that the uncalibrated SOURCE is closer by about 2% to TESIS. And this plot also shows that the full overlap in quiet sun ratios, irradiance ratios, which are our new scaling factors, they both fall within 1 standard deviation of each other. So conclusions. We have identified problematic regions, which has helped us quantify the stability of both instruments. A region of high standard deviation in SOURCE, a region of high standard deviation in SOURCE was found, which resulted in a new diode temperature correction. And the need for a TESIS wavelength alignment was confirmed. We have determined new scaling factors to bring the measured SOURCE SIM radiances to the TESIS SIM calibration. And we have done this for both full overlap and quiet sun periods. And these have been provided for the purpose of generating a new TESIS calibrated SOURCE data product, which is scheduled to be included in the final SOURCE version 28 data release. So future work, what's there left to be done? Can we apply these scaling factors to the entire SOURCE mission? Do the trends seen throughout the overlap, the 2-year-long overlap, apply to the full mission, which was a lot longer, 17 years? And the quiet sun and full overlap scaling factors agree to within 1 standard deviation of the measurement errors. So is there a significant reason to use one scaling factor over the other? So these are questions that need more investigation. And that finishes it up. Thank you very much. Any questions?
All right, thanks. Questions from the audience?
Hi, this is Tom Woods. Can I just ask it instead of typing it in?
Sure.
Thanks for a nice presentation, an overview of those 2 important measurements. So the TSI is very accurate, and when you integrate up the SSI, it's not quite the TSI value because it's not all wavelengths. So if we decrease the irradiance in the infrared, but the TSI is accurate, what is the impacts in the other wavelengths?
That's a good question. Yeah, I'm not quite too sure. More investigation would be needed there. It sounds like it's definitely worthwhile trying that and see what the result is like.
I mean, one comment on that would be, does it pop up in the far ultraviolet or the ultraviolet that we're not measuring? is kind of the question, and how does it impact climate is kind of the other aspect of that that I was scratching my head about.
Mm.
Those are pretty big questions.
Yeah, no, I'm not too sure, but I think it's definitely, you know, up there with the questions that we'd like to, you know, find an answer to as a result of this kind of investigation. I definitely one of the bigger questions, I would say.
So I have a question. If you can go back to slide 8.
Yes.
So in the lower panel where the colors represent the kind of standard deviation. So early, so if we look like in that 1200 to 1600, there's a lot of blue, and then later in the overlap period, it goes to red. Does that indicate a long-term trend between the two data sets? Am I interpreting that correctly? I know that most of your work was just a calibration rather than a comparison of the trends, but I'm just asking if I'm interpreting that correctly.
Which plot are you looking at? Standard deviation,
The lower one. Yeah, kind of in the middle, right? You got a lot of blue, which are positive z-scores, and then you know, as day 600 and so on, there's a lot of red of a negative z-score. So is that a real trend, do you think? Is it statistically significant?
It's a good question.
Okay.
I haven't thought about that.
Okay, that's reasonable.
Yeah.
The other just question about the interpretation of the plot. There's a lot of green horizontal stripes. Do those represent missing data between one or the other? Okay.
Yes. I mentioned it for these plots, but it carries over for these plots also. So the horizontal strips, those are both grids here. The x and y axes, they've been interpolated onto a linear scale.
Okay.
So there's gaps in the days.
All right, that's great. Are there any final questions from the audience? Okay, all right. Let's thank Peter again, and let's actually also thank all the speakers from the first session. We will now take a short break, so you can rest and take off your headphones and stuff. And we will start back up at 20 past. So we'll see you all then.
Just Thanks. A quick reminder, like fill out the evaluation form for Peter, please.
All right, great. We'll see you soon. Hey, Moon Man.
I like the cat in the background of the talk. Bonus.
You ready, Kate?
Yeah, I'm ready. Should I start sharing my screen then?
Yeah. All right, welcome back, everybody. We're ready to start the next block of talks this morning. We'll start off with Kate DeMarche from Scripps College, who is going to tell us about assessing the impact of the Colorado wildfires. All right, thanks.
Great. So hi, my name is Kate DeMarche, and I'm a rising senior at Scripps College. And this summer, I was working on a project about assessing the impact of the 2018 Colorado wildfires on carbon monoxide and the aerosol burden. So just some background on wildfires and their impact on climate and air quality. So the climate changes in the atmosphere increases the annual wildfire area, which then affects the climate in different ways. And these include changes in the disturbance regime through vegetation shifts, albedo changes due to surface changes in the fire perimeter, and radiative and albedo feedbacks from increased emissions of different GHGs and aerosols. And there's also the smoke from wildfires, which contain primary pollutants. And these pollutants include particulate matter, carbon monoxide, nitrogen oxide, methane, polycyclic aromatic hydrocarbons, and volatile organic carbons. And then the wildfires also contribute to the formation of secondary pollutants like ozone. And then air quality degradation from these fire emissions and the secondary pollutants as well is like another factor. And so these effects to climate alter the temperature and precipitation gradients, and this then indirectly increases the number of fire emissions. So also more people then are experiencing unhealthy air spikes in particle pollution in the last 3 years. So more than 53.3 million people suffered from episodes of unhealthy air spikes in counties where they live. And previous studies have cited that wildfires, especially in 2017 and 2018, were a main reason for these spikes in air pollution. So then more of the impacts of wildfires. First of all, there's the health impact of wildfires, since wildfires have been suggested to affect human health. And specifically, exposure from landscape fire smoke has led to 339,000 deaths annually. And particulate matter is the primary concern for public health, since approximately 90% of total particle mass emitted from wildfires consist of fine particles. So fine particles are PM 2.5 or 2.5 micrometers in diameter or smaller. And exposure to carbon monoxide also poses a threat to at-risk populations and then firefighters when they're fighting close to the fire line. And this is because carbon monoxide does not travel far from the point of combustion. So carbon monoxide then enters the bloodstream through the lungs and reduces the oxygen delivery to body's organs and tissues, which is not beneficial for human health, obviously. And there's also the economic impact of wildfires. For short-term exposure, the value is between 11 billion and 20 billion US dollars per year. And a long-term exposure value is between 76 billion and 130 billion US dollars per year. So there's also the correlation between fire and wildfires and climate change. So fire season length and wildfire frequency will increase by 74% of global land due to heat stress from climate change. So there's a growing interest in understanding the population health impacts of air pollution from wildfires, since climate change is anticipated to increase the fire season length and then the frequency of the fires. So there's growing evidence then that the changing climate is making it harder to protect human health. So for the past 5 years, which were recorded as the hottest years in history, with increasing high ozone days and widespread wildfires, it put millions of more people at risk. So especially in the Western US, climate change has made it more likely the conditions of heat and drought to promote these wildfires. And if you're looking at this graph right here, you can see the amount of cumulative forest acres burned for wildfires without climate change, and then wildfires with climate change, which is only going to increase in the coming years. So then more specifically, why we focused on the Colorado 2018 fire season. It was the second most destructive in Colorado history regarding burn area. So some of the reasons for why this occurred was that it was Colorado experienced the warmest forest temperatures in 124 years. And there was also very low precipitation, nearly the lowest since record keeping began. And also the spruce beetle infestation hit 178,000 acres, expanding the total infestation to beyond 1.8 million acres. So this, just as the spruce beetles dried out the trees, it made for conditions that were more likely to cause wildfires. And this is also complicated by the fact that people are moving into areas where fires play a key role in ecosystem health. So it really is the climate change and the lack of the cold temperatures in the winter to kill off the beetles and the hotter summers that made the fire spread the way they did. And some of the impacts in Colorado from this wildfire season was the water supply shortage. So the Colorado forests supply 14 billion cubic meters of water to Denver, Aurora, Colorado Springs, and the Front Range cities. And then when the mountain signs burn and erode, it clogs the rivers and reservoirs. And also 450 homes were destroyed, and it cost about $145 million to fight these fires. And then of course, there were the health impacts from the microscopic particles in the smoke, and that can trigger things like heart attacks and breathing problems. So then specifically, we used several ground-based observation satellites and the global model to evaluate the air pollutants from the wildfires. So for the ground-based observations, we used the EPA air data, air quality monitors, and AirNet. And then for the satellite measurements, we used MOPIT and TROPOMI, which stand for the measurements of pollutant in the troposphere and the tropospheric monitoring instrument. And then we also used simulations from the Community Earth System model. And the pollutants that we focused on were carbon monoxide, because it's a primary pollutant that causes health problems, as well as PM 2.5 is a primary pollutant that causes health problems. And then aerosol optical death, or AOD, which is important for the radiation budget, but it's also well measured, so it allows for a lot more accurate results. And also PM 2.5 and the AOD both can be used then to map the fire season, where peak values could be used to represent a fire event. So then specifically the EPA air data air quality monitors provide surface CO and PM 2.5 concentrations. So there are 7 usable sites for carbon monoxide, which are the blue dots on the map on the right. And then there are 22 sites for PM 2.5, which are the yellow dots on the map just all around Colorado. And these monitors provide ambient air pollution data, and it's collected by the EPA, state, local, and tribal air pollution control agencies for thousands of monitors. So it contains meteorological data and then description of where the monitor is located. And then for AeroNet, which is the aerosol robotic network, it provides the AOD observations. So we used 6 Colorado sites for AOD at 550 nanometers, which as you can see on the graph on the right are just located all around the world. But these provide a database of aerosol optical, microphysical, and radiative properties for then aerosol research. And then we also used the community atmosphere model with chemistry, part of the Community Earth System model. And the global model then simulates the chemicals and aerosols emitted by the wildfires and their transport and interactions with the global Earth system. So looking at the images below, the left is the structure of the grid for the model, and it has the appropriate horizontal and vertical components. And then the right shows how the Earth has many elements. So these elements are similarly coupled in the model, just like Earth, and it divides the complete climate system into the component elements that are then connected by the coupler component, and which controls the flow of data between the different various components. So it has the elements for things like atmosphere, land, ocean, sea, ice, and glacier components. And then by using the community atmosphere model with chemistry, we can then study the climate chemistry interactions. And specifically, we did that for understanding the wildfires and their transport better. So specifically, the questions that we were focusing on is the pollutant increase correlated with the fire season for Colorado? Are the Colorado wildfires responsible for the pollutant increase? And does the global model simulate the Colorado pollutants well? So this first figure shows the daily averages of PM 2.5. And with the x-axis being the month of 2018 and the y being that concentration of PM 2.5. And also on the x-axis, the triangles indicate the time during the fire season when a fire event occurred that was above 100 acres, or a fire event began that was over 100 acres. And then each of the different lines is representative of one of those ground sites for PM 2.5. So as you can see in this late August region, and early August as well, the daily averages increased to levels that were moderate for health and then unhealthy for sensitive groups. So this was a region then that would be beneficial to focus on. So then we focused on looking at the different daily averaged ground observations around Colorado. So with the black line being the average PM 2.5, the blue being the average carbon monoxide, and the red being the average AOD. And then again, with the time that the fire events began are the triangles. And so where there is then a peak value that could be used to possibly represent a fire event. So as you can see, though, there's a positive correlation between carbon monoxide, PM 2.5, and AOD ground observations during the fire season. So then from this, we utilize the community Earth system model to then investigate the reason for that pollutant increase in August that was similarly present in the ground observation averages as for the PM 2.5 for the different ground sites. So to do this, we looked at the carbon monoxide averages in Colorado during the fire season and compared them just for these different variables. So this first red line is those EPA ground observations, then averaged with the appropriate error bars. And then the green line is the model with only Colorado emissions. So those are emissions that only came from Colorado. And the blue line is the model with only background emissions. And then the black line is the model containing all of the different emissions. So as you can see, when looking at this, if we compare the black lines with the blue lines, and again, look at those regions on the x-axis where there were fires located in Colorado, the black lines are increasing during times when there are fires. So then the fires then enhance the CO concentrations. When compared to the model with only background emissions, you can see when there are fires, the model with all emissions then is enhanced in concentration. So then when looking at periods when there are Colorado fires, they are within the EPA observation error bars. And this is indicating that the emissions of Colorado fires then are fairly well simulated. So when looking at the graph here, during the times when the fire, little triangles indicating when a fire begins, are located along these regions. Here, it compares pretty well with the model emissions and the EPA observations, except it is slightly overestimated in July, but otherwise these EPA observations match well, indicating again that the emissions of the Colorado fires are fairly well simulated. So then when looking, when the CO emissions originating from only Colorado fires are low, then the model values are lower than the observations. So on the image here, that is indicated in these regions. So the model with only Colorado emissions then is that green line. So as you can see, when it's at 0, the model with all emissions, the black line is significantly lower than those EPA observations during this time period. And this is similarly found for AOD. So AOD and carbon monoxide simulations show the same underestimation in the period in July and August. So then this is suggesting that fires outside Colorado are the cause of this underestimation. So then we were looking into the reason for this August underestimation. So then this is the satellite observations for these peak days in late August, with the top being the tropo-only satellite and the bottom being the Moppet carbon monoxide and wind satellite information. So the satellite observations then indicate that this fire may be coming from the Canadian region. Specifically, it looked like it was coming from British Columbia. However, there's some of the information meeting, so this would need to be further confirmed with models in the future. So just for conclusions then and future work. So we identified the fire season for Colorado using carbon monoxide, PM2.5, and aerosol optical depth. And we found the Colorado CO emissions is well simulated. And so we think the peak for CO and AOD in Colorado in August is likely the cause of Canadian fires rather than local emissions. So then in the future, we will investigate the transport and lifetime of carbon monoxide and aerosols from the 2018 Canadian fire. So yeah, thank you.
All right, great job. Are there questions? I guess while people are thinking of their questions, I have I think a simple one that you probably explained earlier and I just missed it. So what is PM 2.5? Is it like a mixture of aerosols?
Yeah, so it's like particulate matter 2.5. So it's just the aerosols then that are less than 2.5 micrometers in diameter.
Ah, okay.
Yeah.
All right. Apparently, there's no questions from YouTube. Any other questions from the live audience? No. Okay. Yeah, you did a great job. All right. Great. Thanks. All right. Next up is Chelsea.
Should I start now, or do you want me to wait a couple minutes?
Okay, no, I think so. Hopefully everybody is filling out their evaluations. Yeah, let's go ahead and wait just a moment.
Okay.
Guess I should have introduced this whole session as the atmospheric and planetary session. So we had the atmospheric talk, and next we will begin the planetary pair of talks. Oops. All right. That's probably enough time for people to have filled out their surveys. So let's go ahead and start with our next talk. Chelsea Drake from the University of Maine, Farmington, who will tell us about seasonality of CO2 gas jets on Mars. Thanks.
Okay, hi everyone. As Marty said, my name is Chelsea Drake, and I've been working with mentors Michael and Anya on studying seasonality and CO2.
It's Chelsea. It's difficult to hear you.
Oh. Can you hear me better now?
You started out much louder. Are you far from your microphone?
No, I'm not sure what's going on.
That's much better.
Oh, can you hear me now?
Yes.
Okay,
Thank you.
sorry about that. Yes, so seasonality in CO2 gas jet eruptions on Mars. Okay, so this left image here gives a little bit of background on the CO2 jet processes. So every winter, CO2 condenses to form a translucent CO2 ice slab at the poles of Mars. So when spring comes, solar energy penetrates this layer and sublimes CO2 from underneath. The gas is under high pressure and is looking for ways to escape this CO2 ice layer.
Yeah, sorry to interrupt again. Yeah, your audio is kind of cutting in and out. Is there a cable loose or something?
I am not sure. I'm on my laptop.
Okay. All right. Well, we'll make do. Oh, that sounds very good right now. Don't move.
Okay. Solar energy penetrates the translucent CO2 ice slab, and the high pressure gas breaks through the weakest point in the area, erupting in a CO2 gas jet. So these jets transport darker surface material on top of the ice, which creates features like blotches and fans, and repeated eruptions, erode the underlying substrate, producing the so-called Martian areniform terrain, which we colloquially called Martian spiders. So these processes are not found on Earth. The high-resolution imaging science experiment, or the HiRISE camera on the Mars Reconnaissance Orbiter mission, is monitoring these features and their yearly seasonal reappearance. The data from this mission is providing information on spatial and temporal distributions of eruptions and on the activity levels in different regions of interest around the Martian South Pole. So this up to the upper right is an example of a Martian spider or areniform morphology, and this is an example of some of the fan features we see seasonally. So according to currently accepted models, CO2 jet activity, which leads to areniform or spider formation, is driven mainly by solar energy. So to better understand these exotic processes and their associated features, we developed an overall question, which was, how do surface shadowing and solar insolation influence seasonal CO2 gas jet activity and subsequent areniform formation? So we used high-resolution digital terrain models, or DTMs, produced from HiRISE stereo images together with NASA's SPICE calculations, which gives us the sun's position in the local sky, to produce insolation maps at regions of interest around the Martian South Pole. These insolation maps account for local surface angles, as well as time-dependent shadowing due to topographical features. So the insolation maps we're creating will allow us to correlate the amount of energy that a feature receives to the CO2 jet activity in the area. So therefore, we could potentially determine why some areas are more active or have higher density of areniforms than other regions. So this research will improve our understanding of these exotic CO2 jet processes, which are unknown to Earth, and will improve our understanding of the interactions between the surface and the atmosphere at the Martian southern pole. So this is an example to the right of a high-rise DTM image of Inca City, one of our regions of interest. And this, throughout the presentation, I'm going to be referring to Martian L sub S. So that refers to the Martian seasons or the solar longitude. I'll mostly be referring to L sub S 180 through the summer, which is around L sub S 270. So these kind of orientations. Okay, so our first step was to investigate how changes in surface inclination affect solar energy input. So we picked an arbitrary point to start of latitude 80 degrees south and used SPICE tools to determine how solar flux input and intensity change with varying seasons and surface orientations. So on the x-axis is time. These plots were all created over a full Martian day. And the y-axis is solar flux in watts per meter squared. So the top plot captures energy input at L sub S 184, which is early spring, and the tilt variables refer to the angle in degrees in which the surfaces are inclined from the ground. So a tilt 0 will be a flat surface, tilt 30 is a 30-degree inclination, and tilt 75 is 75-degree inclination. So the aspect angle, or the angle of the surface towards the sun, is 0 on this first plot, which means that the inclined surfaces on this plot are pointing towards the sun. So at this location, the flat surface gets energy first, but overall receives a lower amount of energy than the tilted surfaces. And there is a bit of a jump in energy, as you can see, when we increase the surface inclination. So this middle plot, we have the same season, the same location and tilt angles, but we now have an aspect of 180 degrees, which means that the inclined surfaces are facing south or away from the sun. So the flat surface still gets the same energy as before. It's just scaled a little bit differently on this plot. But the tilted surfaces now have drastically different energy inputs than the plot above. So as the sun rises and sets, these surfaces get small spikes in energy, while the sun is in the east or west positions, but the energy is short-lived as the sun continues, its path throughout the day. And then this last plot shows how solar energy input changes at L sub S 283, which is midsummer. At latitude 80 degrees south, the flat surface gets energy all throughout the day, while the tilted surfaces get energy only for parts of the day now. The inclined surfaces get a higher intensity of energy, but for a shorter period of time. So these plots really illustrate the importance of considering local surface angles while looking at solar energy inputs to the surface. So to develop solar insolation maps for our regions of interest around the Martian South Pole, we had to create many tools with Python that would allow us to determine solar energy input, surface slopes and aspect angles, and topographical information to determine time-dependent shadowing. So two of the most important tools we developed to integrate solar flux and produce solar insolation maps were these simulated flux and horizon map functions. So our simulated flux tool uses Spicer, which is a Python package that allows for easy use of SPICE tools to set up a Mars environment that takes in a date time with a latitude and longitude location and creates a model of the surface based on precise SPICE data. So from our starting time, we loop over whatever time resolution we set up, usually 20-minute intervals over a full day. And then we loop over a specified range of tilt and aspect angles, typically 70 degrees for tilt and 360 for aspect. Spicer calculates the solar flux that the surface would receive based on the specific location, the specific solar incidence angle, the solar constant, the time, and the tilt and the aspect angles. So we save these simulated fluxes for each location and each season. So the horizon map function uses a high-rise DTM and loops over each pixel of the DTM image to determine the maximum angular surface height for each line of sight for each pixel. So each pixel located in, or each pixel location in the DTM is the starting point for calculations. And then we loop over azimuth directions for usually a full 360 degrees around whatever pixel location we're on. So array site function determines the endpoint based on the azimuth angle from the pixel. And the endpoint is always on the border of the DTM image, so we get a full line of sight. We then interpolate the line of altitude values from the start point and end point, and then from there we calculate the max angle of that interpolated line. So this tool really allows us to determine topographical features that would cause shadowing for each pixel in the DTM image that we're looking at. Okay, so using tools like the simulated flux and the horizon map functions, we developed an integration function to produce solar insolation maps at our regions of interest. So this tool uses another digital terrain model with its associated horizon map and its simulated flux values. So the function loops over each time step stored in the horizon map, then over each pixel, and checks if the pixel is in shadow at the time. So if the maximum angular surface angle that we calculated in the horizon map is less than the solar incidence angle, if the incidence angle is greater, I'm so sorry. So if the maximum angular surface height stored in the horizon map is greater than the solar incidence angle for that pixel, then the pixel is shadowed, and then the function moves on to the next pixel. But if the incidence angle is greater and less than 90 degrees, so that the sun is actually above the horizon, then the pixel is getting solar energy. So the function then looks up the slope and aspect angles for that pixel, takes the correct simulated flux based on these features and the current time, and adds the flux to the current pixel location. So the flux is integrated over a period of our choosing, which so far has largely been one full day. Developing this tool was one of our biggest goals for the summer because it allows us to have an image of solar energy input to the Martian surface based on real life surface features and local topography. So before producing our insolation maps, we wanted to see how regions of interest themselves differ with regard to solar energy input over a day without taking into account specific pixel locations on a DTM. So these plots give us a lot of information about how latitude, slope, and aspect affect energy input at specific regions of interest. So these plots are all depicting a full day of integrated flux in joules per meter squared. At LSUBS 184 or early spring and LSUBS 190 or mid-spring. So our simulated flux tool was used to create these for each of the three regions here. On the x-axis, we have the slopes in degrees, and on the y-axis, we have the aspect angles in degrees. So some things to note about these plots. I'll start with the early spring plots on the left side. As we move higher latitudes from 74 down to 87, a flat surface gets less and less energy. So this slope zero line here is basically the flat surface because you can change the aspect of a flat surface and it'll still be flat. So overall, there's subtle changes between Caterpillar and Inca City, but when you get down to Manhattan, which is pretty far south, the energy differences between the flat surface and the inclined surfaces are a bit larger. So the inclined surfaces at Manhattan are receiving more energy than the inclined surfaces at Inca City or at Caterpillar. So when we look to mid-spring over on the right, at LSUBS 190, we see that flat surfaces at all locations are now receiving more energy. And Manhattan in particular is receiving quite a bit more energy than each of the other plots, and definitely more than it was receiving before. All of the aspect angles for this plot are receiving energy, unlike these other locations. So I think this does a decent job of highlighting kind of the unique differences in solar energy input at higher latitude locations. So here they are, the solar insolation maps that we have been working on. After creating more general integrated flux, which we just saw, we used our integration tool to create realistic insolation maps at two regions of interest, Manhattan on top and Inca City on the bottom. So we took a subframe of each high-rise digital terrain model and created horizon maps for each, then put that together with the simulated fluxes for each location. So up top we have Manhattan. Since this image is replicating the surface, both axes are distance in meters. We also created images in degrees of the slopes to compare with the resulting insolation map, and also a small map of the DTM subframe that we're looking at. So this area is largely flat with some small scale topographical features that get a bit more energy throughout the day. So on the bottom, we have Inca City integrated over 1 day at LCMS 184 with 1 meter per pixel resolution. So this image subframe shows a ridge with one side obtaining more solar energy than the other side. So as far as we can tell, this makes sense to us so far, because the northern azimuth for this image is about 9:30, so the over to the left. And as the sun rises, to the north of the image, it crawls, it does its daily path, and then it would set kind of down here towards the south of the image. We really just started making these insolation maps. Some more work needs to be done to ensure that their depictions of solar energy input at the surface are accurate. Ideally, we'll have insolation maps for several regions and for several subframes to compare. Okay, so to recap quickly, using high resolution digital terrain models from HiRise, like this one of Inca City again, together with precise SPICE calculations of the sun's position, we developed tools to produce solar insolation maps for areas of interest around the Martian South Pole. So these insolation maps account for local surface angles like slopes and aspects, as well as time-dependent shadowing due to topographical features. We also developed more general solar flux plots to quickly compare solar energy differences at various regions. So for future work, we need to make more insolation maps and keep double checking those and making sure that they make sense. And then we need to correlate the amount of energy that a feature receives over Martian hours, days, or even a complete season to the CO2 jet activity in the region. So this bottom image is an example of mapping spider features in Inca City, and the goal is to use insolation maps to compare with maps of features such as these to determine if current insolation, is correlated with the density of these arrheniiform or spider features in different regions of interest. So this will give us, more insight as to this this whole process. And that's what I have.
All right, great job. Nice talk. Are there questions? I guess while people are thinking of their questions, I do have a question. Can you go back to the slide that has the plots of the solar flux over a day?
These ones?
No, back. That one.
Ones, yeah.
Yeah. So I'm trying to understand the middle one. So can you walk me through what those spikes in the morning and evening are from? What causes that?
So I believe, and if my mentors are on, they can correct me if I'm wrong. I believe so. These spikes are So when the sun is, the tilted surface is turned to the south, that surface gets a smaller amount of energy as the sun is rising or as the sun is setting, and it only gets kind of a spike for a short amount of time because it doesn't receive that much energy, and then it kind of goes flat again.
So is that when the sun rises and when the sun sets? Is that what the timing is?
I believe so. I don't know if Michael or Anya are on. And
yeah, so we think this is just really the vectors. It's a vectorial situation where the sun is just far enough away from north that the tilted aspect surface that looking at south just catches it when it's fully east and fully west. It's just far away enough from north that there's a little bit of energy coming to that surface, even though it looks to the south. It's just like lurking around the corner. The sun still gets the surface. But then, because you're at the South Pole, the sun moves during the day towards the north, and that south-facing surface doesn't see anything. And then at sunset, the same happens. It just lurks around the corner of that south-facing surface.
Yeah, Anya is here. I just want to add, maybe people missed it, that we are in the southern hemisphere. So looking to the south means you look towards pole. Looking to the north, means you look towards the actual sun. So that how we say here, looking to the south is always sun facing. So that's why when this surface tilted towards the pole, that means it's missing all the lunchtime sun, which comes from the north in this case, or from the equator. So it's every time a little bit mind-bending to think about the southern hemisphere.
True, true. So there is a question from YouTube that I will try and. So they're asking about the solar cycle terminator. So I don't know if this is Scott McIntosh on there. So their question is, will this work for the terminator? Maybe. So I'm struggling to understand the question. So maybe I can ask a clarifying question about the solar flux. Is this essentially just a solar constant then modeled for the distance and geometry of the position, or is this a particular wavelength?
No, this is basically the solar constant in total in watts, and then just precisely modeled for its local position.
Okay.
Well, does it not depend if SPICE actually has it or not? I think the SPICE can have the solar cycle.
I don't understand your comment at all. What are you talking about?
The variation of solar constant with time, basically.
That's just done via distance.
No, yeah. I mean, it can include it. The SPICE can include the variation of solar cycle. So basically measured real solar constant, not just one number modulated by the distance.
SPICE doesn't have that kind of physics.
Yeah, well, even if it does, I mean, the variation, if this is essentially the integrated spectrum, it's only going to vary by 0.2% over the solar cycle. So that's probably not.
Probably for us, it's not important.
Yeah.
Okay. All right. So yeah, I'm not sure I understand the question.
Yeah, I mean, our intent really is to calculate the energies over all time at a specific location, while the terminator is something that walks over the planetary surface. So I don't understand the connection.
Okay, so maybe the questioner can send an email later and we'll try and understand that. We have apparently answered the question, so that's good. All right. If there aren't any other questions, let's thank Chelsea again. Nice job.
Thanks, everyone.
All right, and then people can fill out the evaluations while Colleen gets set up. Okay.
All right, are we good?
I think so. Yep, we can hear you. All right. So our next planetary talk is Colleen Everett from the University of Southern Alabama from USA, and she's going to tell us about the reflectance of Saturn's rings. Thanks.
All right, thank you. All right, so like Marty said, my name is Colleen Everett. I'm a sophomore at the University of South Alabama, majoring in physics, and I'm currently a student researcher in the Boulder Solar RU program. My mentors, Marty and Josh, are researchers at the Laboratory of Atmospheric Space Physics at the University of Colorado Boulder. Our research project is based on the ultraviolet reflectance phase curve of Saturn's rings. All right, so I'm going to kind of ease you in a bit and give you some facts about Saturn that you may or may not already know. Saturn is the second largest planet in our solar system, second to Jupiter. And like its big brother, Jupiter, it's mostly made of hydrogen and helium gas. Its rings are kind of a different story. Their length spans to 175,000 miles, but the thickness of the rings is said to be only like 30 feet thick. It's the most distant planet that you can see with the naked eye, and it takes nearly 30 years for Saturn to orbit the sun. One day on Saturn is equal to 10 hours and 14 minutes on Earth. That means that this huge planet that has a diameter of 30 Earths is spinning extremely fast. And a little fun fact that Saturday was named after Saturn. So there's many things that could be said about the Cassini-Huygens mission, so I'll kind of have to just break it down with a few highlights. Cassini was first sent into space June 30th, 2004, passing by Venus twice before slingshotting into the outer solar system. It took 7 years for Cassini to reach Saturn, which is its main mission, but it didn't miss opportunities to take pictures along the way, like any traveler would do on an epic road trip. When it was coming up on Saturn, it revealed that there were more rings, and they're very faint, and they could be seen, which we'll show you, or I'll show you on the next slide. During its mission to Saturn, it hurled the Huygens spacecraft toward Titan so that it could land on Titan and take samples of its methane lakes. As it orbited around Saturn, it studies the rings, Saturn's moons, and saw many different phenomena, like these two storms molding into one, and one huge storm hitting its own tail and fizzling out. And my favorite, the hexagon-shaped storm at the North Pole of Saturn that we had never seen previously that I'll show in the next slide also. After 13 years of orbiting Saturn, it was time to let Cassini go. So scientists urged Cassini to orbit between the rings and the body of Saturn, eventually leading to its demise on September 15th, 2017. Now, another fun fact is Cassini was named after the famous astronomer Jean-Dominique Cassini, who weirdly enough died on September 14th, 1712, just a day before they crashed Cassini many years ago. So coincidence? Who knows? Here are those pictures I was mentioning in the previous slide that show some of the wonderful observations and discoveries Cassini has done. On the left here is a picture that shows Cassini passing in front of not only a side profile of Saturn's rings, but a Titan in front of them. On the bottom right is a picture showing the faint rings that Enceladus caused because of its plumes of water coming from the surface. Also, if you kind of look at the B ring of Saturn, it is the dimmest one in this picture, and the other rings are brighter. This is because the photo was taken during the eclipse. Normally, we would see B ring as the brighter ring, but because of its backscattering properties and forward scattering through A and C rings, the opacity of Saturn's B rings appear to be dimmer. Last but not least, on the top right here, this movie shows the hexagon-shaped storm rotating that occurs in Saturn's North Pole. Okay, so we have some terminology I want to go over before I explain the ins and outs of my project. Let me first explain the terms on the left over here. Spectral dependence basically means, in this case, that the brightness of the rings can change with wavelength. This is the basis of our question, which I'll go over in the next slide. An example of spectral dependence is if you look into a mirror from different angles, do the colors you see change? What about when you look at a CD from different angles? Do those colors change? You do, in fact, not see your reflection change colors, but the CD does change colors because it depends on the wavelength. We want to know whether Saturn's rings do this. The phase curve essentially shows the magnitude or brightness of the object being observed as a function of phase angle. And with that information, we can better understand what the surface properties are. As for the terms on the right, they're explained in this picture below here. If you look at the picture, you can see that the sun and the instrument are at different angles, right? You see those angles by the shadowing that's occurring on the left side of the photo and the brightness on the right side. And of course, the angle at which you're viewing Saturn. So the first angle is the emission angle, I, which is the angle the light is hitting the instrument. The second angle is the incidence angle, which is J, and that is the angle that the sun is hitting the rings. The phase angle G is the angle between the sun, the rings, and in this case, the Cassini-Uvis instrument. Ideally, I would have had an arrow pointing at us, which are the observers viewing this image, as if we were Cassini, which would be the emission angle. However, I depicted it like this instead for viewing purposes. This is an example observation of the UVIS B-ring FUV spectrum. The units of measurement on the y-axis here are kilorays per angstrom, which is found by multiplying the raw data by the calibration matrix. The wavelengths on the x-axis is shown in angstroms. Kilorays per angstrom is the number of photons per second per solid angle. So for different wavelengths, we get a different number of photons per second. So our big question is there a spectral dependence on the reflectance phase curve of Saturn's rings? The reflectance phase curve has been calculated on planets to understand the surface properties, but we have not kind of done so in such a high spectral resolution in the far ultraviolet with Saturn's rings. Scientists have done this with infrared data and using lower resolution instruments like Voyager, but they haven't specifically looked at the far ultraviolet with Cassini-Uvis and solar solstice. When trying to understand what we're looking for when it comes to the reflectance phase curve, let's think about a smooth metal surface and a rough metal surface. The smooth metal surface indeed reflects more light than the rough metal surface. As shown in figure C, on a flat shining surface, incoming rays all reflect in the same angle direction, and they don't scatter. However, on a rough surface, the incoming rays reflect at different angles and are scattered in different directions, just like I explained with the mirror and CD on the fifth slide. It can also be understood through figure A and B, where the flower in this case is perfectly reflected in the smooth water, but the flower is distorted in the rough water. As for Saturn's rings, calculating the reflectance phase curve can show the composition and particle sizes of the particles in the rings based on the way that it scatters in the far ultraviolet spectrum, and helps us answer whether there is in fact a spectral dependence. Now, remember, spectral dependence means that the brightness can change depending on wavelength. So answer this question in your head and see if your hypothesis is correct at the end of my presentation. Do you think that there is a spectral dependence? Just be patient, we'll find out. So here's a little bit about our research process. Using Python 3, we created code that imported raw UVIS data, subtracted the noise, calibrated and interpolated the cube data, along with removing the NAND variables, which are variables that are not a number in the data set. We then converted the units of each spectrum to reflectance and divided the UVIS spectrum by the solar spectrum. We overplotted a straight line onto our scatter plot before we introduced Hatke's calculations into the mix, which I'll show you later. And then we applied that Hatke's calculation, and then we got our phase curve. Focusing on Saturn's V ring, we first saw a representation of that data we had analyzed taking form here. We plotted a combined scatter plot of each wavelength to look at the brightness as a function of phase angle. We first experimented with a line which just basically put a line through each wavelength and gave us an idea of whether the curve may change based on wavelength. When we look at this image, you can see each wavelength change with respect to phase angle. And when we think of our initial question, is there a spectral dependence? This kind of almost looks like there may be. The image prior was from a 4 to 13 degree phase angle. However, this image is a collection of observations on a scatter plot with a line applied. Using our B-ring spectropixel locations, we calculated the phase angle using the cube generator software, which utilizes SPICE kernels. As you can see here, this line no longer works. It's not showing you an accurate representation of the slope. We needed something that was much more accurate, so we looked to Hatke and his calculations, which I'll show you in a little bit. Here are a few pictures that show how we calculate reflectance and what it looks like before we do so. The picture on the left shows the solar spectrum from the solar solstice instrument. The solar spectrum changes by day and also by location. This observation, of course, shows Lyman alpha at close to 120 nanometers and an increasing solar irradiance from 160 to 190 nanometers. The picture on the right here is the UVIS B-ring calibrated spectrum. The units of measurement here are kilorays per angstrom, which is found by multiplying the raw data by the calibration matrix. You can also see here that Lima alpha is present at around 1200 angstroms, and the brightness working its way up from around 1650 to 1900 angstroms. In order to get the phase curve, we had to convert the units of each spectrum to reflectance and then subtract the solar spectrum. So when we take these two things, I, which is the UVIS spectrum, and F, which is the solar spectrum, and we divide them out. Reflectance, or I over F, is a ratio of how much light is reflected back to how much light is actually on the rings. Kind of like that example I was talking about earlier with the flower and the water. This Cassini UVIS FUV B-ring spectrum example shows us that it reflects light differently depending on the surface properties. So some of you may be going, well, what does this even show me? Just like the others, it still has some fog from Lyman alpha in this lower graph. If you look around 1650 angstroms, you can see a steep incline there. We know from looking at materials here on Earth that water ice has this shape, which is why we think that this is water ice being shown here. Sometimes this ramp is called a red edge because in this case, it is toward the longer wavelengths. If this was a blue edge, we would see an incline at shorter wavelengths. There's about 5%. There's about 5% of the particles of the rings that are currently unknown. Maybe we'll find some selenium in there someday. Hapke's equations are ways to describe different phenomena that occur. The first equation is the full form of Hapke's equation, which kind of makes your head spin, doesn't it? That's all right, it can be explained. The quantities that we measure are W, which is the albedo or brightness, mu, which is the cosine of the angle of emission, which is the angle at which the light is hitting the instrument. Mu naught is the cosine of the angle of the incident light from the sun to the normal vector. And to explain a normal vector, it would point away from the surface. Many of these parameters are fixed parameters based on work done by others like Todd Bradley. So we aren't calculating them, just inserting their values into the equation. The second equation describes the average slope angle, theta bar. S refers to the large scale properties of the surface. The least square's best fit has theta bar as a free parameter. In this complicated equation, theta bar represents basically how bumpy the surface is. So if we looked at that smooth and rough metal surface picture, this is what theta bar is trying to explain. When theta bar is 0, the surface is smooth. And when theta bar is much bigger, the surface is bumpy. Here we have some UVIS files read into a Python function that displays an image showing Hapke's best fit curve plotted on top of the reflectance scatter plot. Something that was explained to me was that the brightness at phase angle 0 is much more apparent at higher phase angles. At a phase angle of 0, the object observing tends to reflect more light, showing a higher brightness than at other phase angles. This is really apparent at 1600 to 1900 angstrom wavelengths, where the phase curve is much more prominent. Theta bar here in the legends of these plots are basically measuring the mean surface roughness. It's what I mentioned earlier in Hapke's equations. The best fit phase curve makes the function match the data as best as possible. Like the pictures, like the pictures of the flowers, you can see the reflection changes based on the roughness of the green particles. Reflectance, or I over F, values show basically what the ratio is reflected back. And here we have our results, our bread and butter. So I combined all the Hapke best fit theta bar phase curves and plotted them together on the same plot, as you can see here. Both of these images show reflectance as a function of phase angle. However, figure B over here shows a zoomed in version of figure A. Looking at Lyman alpha, which is the green line behind the blue one, it's relatively constant and doesn't keep going up like the other curves. 1200 kind of behaves similarly because of the fog that Lyman alpha is giving off. All of this shows the wavelength dependence of theta bar. So you're probably like, okay, but what does theta bar represent? So it represents the average slope angle, which describes the large scale roughness. Another way to look at it is if you were thinking of hiking a mountain that goes up a peak, theta bar would represent the average slope of that hill, which would describe what that hill is made of, whether it be rock, ice, or even sand. If you look at figure A, you can see that at phase angle 0, more light gets reflected back than at higher phase angles. That means that each phase angle changes with respect to wavelength. So I know I asked you guys earlier whether you think that there's a spectral dependence on the phase curve of Saturn's rings. The answer is yes. There is a spectral dependence that is clearly seen in these graphs. So what will the future look like? We will finish calculating the reflectance phase curve on the A and C rings of Saturn. We started with the B ring data because it was brighter, but now that I know how to do all of the calculations and the code and all that, it should be easier to include data from other rings. We'll need to solve for other parameters in Hatke's equation. And now that we've calculated theta bar as a function of wavelength, we can look at different materials and see if it pulls out anything else besides water ice, like rock, dust, or colonium. After that research is completed, we would then need to write a paper about our findings on the A, B, and C rings. Thank you. Any questions?
All right, nice job. Are there questions from the audience? None so far. People say it's cool, right? We're all like, whoa, look at that hexagon. All right, Megan, applauds your good job of explaining things. I also will applaud that. I think all the questions that I was going to ask, probably I asked yesterday when we were practicing this. So it's good. Any other questions from the audience?
Actually, I want to ask one question. This is Anya
Yes.
Kortyankina.
Uh-huh.
Do you envision these techniques that you're using here being applied to other rings? If we have ever another mission to the planet with rings, do you think you can use your work there?
Do you think that if we could use my code to use it for other rings?
Yeah.
I would like to believe that we could. I plan on doing the A and C rings, and I would hope that we could use these calculations and this code.
Which instrument would you like to fly then? Same as UVIS?
I mean, I don't think I have a particular instrument that I prefer anyway.
Okay.
I think Anya's question is sort of, was there anything that the UVIS data didn't provide that you wished it did, or did it produce all of the appropriate data?
Yeah, thank you, Marty.
Oh, I'm sorry that I didn't understand that. I apologize. So far, I think it gave us the answers that we were wanting and that I had the time to, get. But I don't know the answer to that with future stuff. I know that we're going to be looking at the surface properties and things like that later. So I think I'd probably better be able to answer that later on in my research.
Mm-hmm. All right, very nice. All right, let's thank Colleen again. Good job. All right, so next we have another break, and we will start at 10 till the top of the hour. So at 11:50 in the Mountain Time Zone and something 50 in your time zone. So we'll see you in about 20 minutes. everybody's camera off. I don't know if you've come back yet or not. Ah. Look at everybody zooming in. Even Moon Man has returned. Everybody's camera off. I don't know if you've come back yet or not. Ah. Uh-oh, some long delay. Pancakes? Kennedy made pancakes? All right, Izzy, you're up next. You wanna get set up?
Okay. Let's see. Can y'all see my screen?
Yes.
Let me get all the Zoom stuff out of the way. Okie dokie. Am I cool to start?
Yeah, I'll introduce you. Welcome back, everyone. The next talk will be by Izzy Huckabee from Arizona State University, talking about ultra relativistic electrons. Take it away.
Yeah. Hi, I'm Isabella Huckabee. I'm a rising sophomore at ASU, and with my mentor Hong Zhao, we did a statistical study on the ULF wave-driven ultra-relativistic electron flux oscillations in the outer radiation belt. So that was a lot of words, but let's just jump into it. So this diagram shows the many components that make up the Earth's magnetosphere, and we're going to be focusing on the inner magnetosphere, which consists of the overlapping regions that are the plasmasphere, ring current, and radiation belts. In this diagram, the radiation belts are represented by the trapped particles in that white circle on screen. The locations of the regions overlap, so where they differ is in the populations of their charged particles. So to investigate the particle populations in the radiation belts, we employ the twin Van Allen probes, which are able to traverse the belts one behind the other in a matter of hours. These probes have highly elliptical orbits and come as close as 375 miles from the surface and go as far as 20,000 miles. So they're able to explore a lot of the locations in the radiation belts. In this study, we utilize the Relativistic Electron Proton Telescope, or REPT instrument, aboard the probes made for detecting and measuring the flux of relativistic particles. The REPT instrument can measure the fluxes of high-energy electrons up to 20 MeV. So, within the inner magnetosphere, particles are moving in three distinct ways seen here. First, we have cyclotron motion, in which the particle gyrates around a magnetic field line. Next, we have bounce motion, where we have oscillations between mirror points in the southern and northern hemispheres. And finally, drift motion, where the particle drifts around the planet along something called an L shell. This is basically a measure of distance from Earth. So the larger the L shell, the farther the particle is from Earth. When changes in the electric and magnetic field are slow, the L shell an electron is on is conserved. However, if the frequency that the field is changing at is near the frequency that the particle is drifting at, we might get resonant interactions that violate these conservation conditions and see electrons that move inward or outward. This is an example of these motions in action, along with the orbit of the Van Allen probes. Without disruptions, the electrons maintain their L shell or orbital distance from Earth, but with resonant interactions, that changes. We know that ultra-low frequency, or ULF waves, cause the necessary fluctuations in the electric and magnetic field that violate this conservation condition. And this violation leads to the movement of electrons inward or outward across L shells. This movement is called radial diffusion, which is the transport of electrons that are accelerated by ULF waves to MeV energies. We can visualize this for an MeV electron interacting with the ULF wave of wave mode 1 and with a frequency that matches that of the electron. So the X and Y axes indicate distance from Earth, and we see that the electrons in ULF waves experience a resonant interaction, and over time, some of the electrons are thrown inward and some are thrown outward. As you can see here, at t equals 90, the particles noted in red are being thrown inward, and the particles noted in blue are being thrown outward. So ULF waves with frequencies the same or greater than an electron's drift frequency can cause variation in the electric and magnetic field and interact with electrons through resonance with their drift periods. And that interaction then causes radial diffusion, which moves the electrons either towards or away from the Earth, depending on the distribution of particles at the time. So radial diffusion works to smooth that distribution out. The question is now, why do we care? Well, we place a lot of satellites in the inner magnetosphere. Energetic particles can penetrate and cause failure in electronics aboard spacecraft, and can also damage the bodies of astronauts if not properly shielded against. We don't fully understand the acceleration mechanisms for ultra-relativistic electrons in the radiation belts, or just how much radial diffusion contributes to that acceleration. So in order to understand the larger environment of the universe, we must first understand the local environment that we're putting our instruments and astronauts in. So we can detect radial diffusion by detecting the fluctuations in the fields that cause it in the first place. But recently we found that oscillations in the flux of these electrons are also correlated with radial diffusion, such that we can use electron flux oscillations as an indicator of radial diffusion. So on the left, measured by the REP instrument, we're displaying electron flux over time for different energy channels. We have an example of what an electron flux oscillation event might look like for the 3.4 MeV channel in black and the 4.2 MeV channel in blue. Overall, flux isn't what we're looking at, but rather the periodicity and the amplitudes. So if we can automatically identify these flux oscillation events and when they're occurring, we can then look at other parameters at these certain times to try to squeeze out a correlation between times of these oscillations and, let's say, solar wind speed, magnetic field strength, location, etc. So the question we want to ask isn't necessarily about the flux oscillations themselves, but rather under what conditions they are occurring in. And because we can use oscillations as an indicator of radial diffusion, we're basically asking under what conditions radial diffusion is happening. And before we get started, we need to understand what other parameters the telescope gives us. So it gives us flux over time, the L shell that the probe is in, and then something called magnetic local time, or MLT. So we have a system for magnetic latitude and longitude that converges at the magnetic poles rather than the geographic ones. So points with the same magnetic longitude will have the same magnetic local time. So an MLT of 12 will be upwind facing the sun, and an MLT of 0 or 24 will be in the opposite direction, downwind. But for now, we're going to look at this and ask, what makes this an electron flux oscillation event? Why are we saying that we know oscillations are happening in the 3.4 MeV channel in black, but not in the 7.7 MeV channel in red? Well, first of all, we can see clear amplitudes. We can point out clear peaks in the 3.4 MeV channel. Second, it's the periodicity. The period of oscillation corresponds to the expected drift period for these particular L shells and energies, which is 4.4 minutes for a 3.4 MeV electron at an L of 5.2. So now let's look at a background event to make the distinctions clearer. In this, the flux over this interval certainly isn't smooth, but there aren't multiple discernible peaks, and there are no oscillations on timescale that resemble the drift period for these particular L shells that the probe is traveling in. So here it's from L equals 5.9 to 5.6. We found that a pretty good way of identifying these events is through something called a fast Fourier transform, or FFT. To do this, we take something called a discrete Fourier transform, or DFT, which takes a data vector, rather than a function, a data vector, small f, and asks how much of this vector is in the sine direction and how much is in the cosine, much like you'd parameterize something into x and y components. Once we do this, we get our transform big F. So the FFT isn't actually what we're computing. The FFT is the mechanism in which we efficiently compute the DFT. And the result of this is converting a time domain to a frequency domain. And so at the bottom left, you'll see like a little graphic I made demonstrating the transform. And so the transform tells us the magnitude in each frequency. So f sub 0 gives the magnitude of the lowest frequency, and f sub n gives the magnitude of the highest frequency. And if we visualize this, we'll get a plot that has a power spectrum on the y-axis and frequency on the x. And we have this here. So on the left, we have our electron flux oscillation event, and on the right, an example of a background event. And the vertical line indicates the frequency that corresponds with the drift period of the electrons at this time. So the line is going to be different and will shift with each time period based on where the probes are. We already see obvious differences. The electron flux oscillation event demonstrates greater power overall and a peak around the drift frequency. So these features are what we want to look for when we start identifying these events automatically. So these are our identifiers of an electron flux oscillation event. So number one, it needs to be distinguishable above the background noise. We need to be able to make out that periodicity in amplitudes. And so what that means is for the 3.4 MeV channel flux that we're looking at, we need that to be above 200 per centimeter squared per seconds per steradians per MeV. And we'll go through all this visually. Next, we want an elevated magnitude of power. So in numbers, that means within 0.55 millihertz of the drift frequency, our normalized power must be greater than 10 to the negative 3. And finally, we want a pronounced peak in power. So the ratios of the maximum and minimums on either side of this interval, we want it to be greater than 2.3. And all these numbers, so the 0.55, the 2.3, those have come from trial and error. So which number is enough to filter out the non-events and to maximize the number of actual events that we find. So visually, this is what it looks like. We're looking at overall flux. So if we were to filter out all the fluxes below 200, this is what we get. So we'd be able to totally filter out this background event, or at least most of it, and then keep this electron flux oscillation event on the right. Next, we're looking at normalized power. So if we are to filter out all of the events that have powers less than 10 to the negative 3 around the drift frequency, this is what happens. We're able to totally filter out the events on the left and then keep that peak and identify that oscillation event on the right. And finally, we have pronounced peak. So both of these graphs actually have peaks around the drift frequency. But as you can see for the event on the left, it's more of a blip rather than a peak. And we know that it's non-event because we checked. We visually went and looked at the flux versus time graph and checked if it was an oscillation event or not. And it wasn't. So we want to be able to see that peak. So we said that a maximum within 2 millihertz of the drift frequency must be 2.3 times greater than minimum values on either side. And so after we ran a bunch of times through this criteria, we got that for the year of 2017, 448 30-minute time intervals that we identified. And so we considered oscillations within a 2-hour time period to be one event because we were identifying, let's say, 1:32 to 2 and then 1:35 to 2:05. And these are the same event. So we basically condensed that and grouped it together to have a list of different events. And we were able to find 272 of those. But future analysis might consider a longer time period to count as one event, such as grouping oscillations within a 24-hour time period, because this may yield different results as we start looking at solar, wind, and geomagnetic conditions during these oscillation times. So on the left, we plotted the conditions that were present at the same time the flux oscillations occurred, and on the right, we plotted the conditions for all of 2017. In general, the satellite spends more time in higher L shells, and we usually consider the L equals 5 to 6 range when thinking about relativistic electrons, because their drift periods would be too fast to detect for lower Ls. In this, we see that there are electron flux oscillation events going on in the lower Ls. We also see a drop-off at those Ls approaching 7, but that is due to lack of data at those Ls. We see similarities for the MLT, which again, an MLT of 12 faces upwind and an MLT of 0 or 24 faces downwind. Initially, we don't see that much of a difference between the oscillation events and the whole year, but we definitely want to run this algorithm on a larger timescale to garner a big enough sample size to analyze this further. Same thing here for the Z component of the magnetic field. We don't see too much difference, but again, we'd like a larger sample size before we conduct any quantitative statistical tests. So the distribution of solar wind speed during all time in 2017 and during just flux oscillation events is very different. On the right, across all of 2017, we get a left skew with a median of 424.7 kilometers per second. However, our distribution of speeds during times of flux oscillations is both multimodal and features a right skew. The peak in the higher speeds agrees with previous studies that there is a positive correlation between solar wind speed and ULF waves that drive these electron flux oscillations here. Now we have solar wind pressure, and the plots again look similar, but we can note that electron flux oscillation events are occurring during both times of high and low pressure rather than just high pressure, because a greater solar wind pressure can cause an interplanetary shock, which can trigger ULF waves. But this doesn't happen often enough for us to discern any significance from this data set. So, but what this tells us is that we have radial diffusion going on, not just during these times of high pressure interplanetary shock. Moving on to the AE index, we can use the AE index as a proxy for substorms. So the higher the index, the greater overall activity. So looking at the two medians, we see that during electron flux oscillation events, the index is considerably greater. This is actually really interesting because we know that substorms have a direct role in accelerating electrons in the radiation belts, but they do this by providing populations of electrons to the radiation belts. And so seeing an elevated AE index for ULF-driven electron flux oscillations, this may suggest that substorms play a role in triggering ULF waves as well, not just by supplying populations of electrons, which then results in radial diffusion. But again, we need a larger sample size to do further analysis. So now moving on to the SIM-H index, this is a proxy for ring current activity, which causes geomagnetic storms. So the more negative our SIM-H value, the stronger the geomagnetic storm should be, starting around negative 20 nanoteslas. We do see a more negative SIM-H in the events, but this could also be a result of how we grouped our events together. We'll see some lag time between the storm measurements and the flux measurements. So if you only catch the beginning of events, we may be missing out on more interactions. Another thing that may allude to a grouping problem is that for our oscillations, we're seeing a lot of positive SIM-H values. We see positive values sometimes during the initial phase of a geomagnetic storm caused by interplanetary shock. So this may indicate that we're missing the main and recovery phases of these storms in our basically derivation of these flux oscillation events. So to summarize this study, electron flux oscillation events occur during times of increased solar wind speed and AE index. So firstly, that confirms that oscillation events are indicators of radial diffusion, because we already know that fast solar wind speeds are well correlated with radial diffusion already. So to see greater speeds with our flux oscillations as well simply further establishes the relationship between flux oscillation events and the radial diffusion. Secondly, the increased AE index indicates that substorms may trigger ULF waves. We know that substorms accelerate particles by supplying populations of them to the radiation belt, but now this increased AE index indicates that the substorms may also trigger ULF waves known to drive our electron flux oscillations, which then in turn accelerate electrons via radial diffusion. With both of these parameters, we need a larger sample size to run any sort of statistical test. When it comes to dynamic solar wind pressure and SIM-H values, the two are actually related in a way. During times of high pressure, we see positive SIM-H values due to interplanetary shock. During times of low pressure, we see negative SIM-H values. And during electron flux oscillation events, we're seeing both high and low solar wind pressures, positive and negative SIM-H indices. So this suggests that radial diffusion doesn't just happen during interplanetary shocks. We know that these interplanetary shocks trigger ULF waves and cause radial diffusion, but this lets us know that it also occurs outside of those high pressure positive SIM-H times. But again, we'd like a larger sample size. This brings us to our future works. So I've been talking about, we need a larger sample size, So what we want to do next is get that larger sample size. We want to run this algorithm on all measurements from 2012 to 2019. And this will give us that sample size we want to run statistical tests on. And we ultimately want to test if there is significance in the elevations of solar wind speed, the AE index, SIM-H index, etc. Also, we want to alter the code to use a different timescale to count as one event. Right now we're using 2 hours, but we might want to use 12 hours or 24 hours. This may seem minor, but some of the parameters have lag times. The data we see at the beginning of the event may be different from the middle or end of it, especially when it comes to geomagnetic storms, where it happens in phases with different solar wind and geomagnetic parameters for each phase. Some broader questions we can ask are, how exactly are the amplitudes of the electron flux oscillations correlated with the ULF waves? Because when we identify these events, or oscillations, we're affirming that they have some sort of periodicity to them, but we haven't really touched on their amplitudes yet. Do stronger ULF waves trigger higher amplitude electron flux oscillations? That's what we want to know. Another question is, why don't we see these oscillations all the time? So radial diffusion in some way or another is occurring all the time, not just during our oscillation events. So must we reach a certain level of radial diffusion before we see these electron flux oscillations? So a larger, steeper gradient in particle distribution means stronger radial diffusion. So where exactly is the point at which we see flux oscillations occur? How steep does that particle distribution gradient have to be? These are some of the many questions that are plaguing radiation belt research. But that's all I have, and I'd like to thank you for listening to my presentation. Here's some of my acknowledgements too. And if you remember, this is the cartoon that we made at the beginning of the RU. Thank you.
All right, nice job. Are there questions? There's there's a question from YouTube that I'm trying to understand. So the question asks about X-ray flux. So you've shown a correlation with solar wind speed. Do you also use solar irradiance measurements in this, or does
no,
that not?
That would be something interesting to look at, but we just looked at wind speed and pressure, unfortunately.
Okay, so I actually have a question about that. So so you showed a plot of all the wind speeds, and then the wind speeds where there are yeah, this one, perfect. So it looks like all the events happen when the wind speed is pretty high. Can you just use wind speed as a predictor of whether there's going to be an oscillation event? What, have you looked at like the probability of like, okay, well, the wind speed is 600. What fraction of the time does that create an oscillation event?
Yeah, that'd be something interesting to look at. So, but also if we're looking at the counts, so so let's say it's 600. So across all of 2017, we have about almost 4,000 counts of this like 600 kilometers per second wind speed. But just with 2017, it's only about 10 that we identified. So just because we have a...
And just to ask a clarification of the plot. So counts means number of events?
Yeah.
Okay, yeah.
And so just because we have a increased solar wind speed doesn't necessarily mean we have electron flux oscillation events. Oh, what happened? There we go.
There we go. Yes, but they're somewhat statistically correlated, right?
We'd have to do some tests. So this is just based off median. We haven't been able to run any like actual quantitative tests yet, but that's something we'd like to do in the future. And I guess that comes back to our question of why don't we see electron flux oscillation events all the time? Because we know that radial diffusion and increased solar wind speed are correlated.
And I guess since I'm not seeing other questions pop up, I will ask one last one. So so it's so you got a measure of the solar wind speed, but there you could also know how big a variation that is. I mean, is it is the solar wind very smooth at high speed, or is it more choppy? And I wonder if that's another thing that may would short time scale variations in the solar wind be more likely to cause oscillation events, or are those unrelated?
Yeah, I'd like to see that too.
That's perhaps a big question.
Yeah, that is really interesting. That'd be cool to look into.
Yeah,
okay.
So this is Ho, and I want to comment on that question.
Yes.
So that is definitely a great question. And actually, until now, a lot of studies have found that both solar wind speed magnitude and just like you said, delta V, how fast the solar wind speed changes correlated with the UF wave UF wave power measured in magnetosphere. So yeah, that's definitely a great idea to later on look at that power, and we can see run our statistical tests, see which one actually correlates better.
All right, very nice. If there's no follow-up questions, then let's thank Izzy again. Good job, and take a couple of minutes to fill out the evaluation while Jake gets set up for the next talk. You're just trying to entertain the cats who are watching, right?
Yep. 20 screens attacked by cats today.
So you're very faint.
I'm very faint. Okay.
Yeah, I can barely hear you.
Yeah, let me try something. Oh, it turned me down super far. Okay, is that better?
Okay, that's getting better. That is much better.
Okay.
All right, cool. All right, so our next talk is from Jake Wilson from University of Maryland, and he's going to tell us about solar wind.
Yep. So, my name is Jake Wilson. I am a junior at University of Maryland College Park, and my mentors for this summer were Craig DeForest at Southwest Research Institute, Barbara Thompson at NASA Goddard, and Sarah Gibson at the High Altitude Observatory. So the first thing I need to tell you about is something called PUNCH. So what is PUNCH? PUNCH is a mission called Polarimetry to Unify the Corona and Heliosphere. So what does that mean? Well, the corona and the heliosphere are these two kind of separate things right now, but in reality, they are probably linked together by relationships through how they work. So we have solar physics, which studies the sun and solar corona primarily through remote sensing and spectral analysis. So an example of that would be like LASCO C3, which is a coronagraph. Then there's heliospheric physics, which studies the solar wind in interplanetary space primarily through in situ sampling, which is generally looking at data more than images. So how does PUNCH work? So PUNCH is made up of 4 main imagers. There is the near field imager, which you can see in this red circle right here, which is fairly close to the sun compared to the 3 wide field imagers. Now, these 3 wide field imagers are always overlapping inside of this blue circle. So that creates something known as the rapid field of view, which you can see in this image, where every 4 minutes we have a new picture. And then in this outer region, we have this composite field. And how this works is that the wide field imagers rotate every orbit. So once we have enough images, we can then create a virtual instrument by stitching all of these pictures together into a single composite image. So that allows us to have a new image every 32 minutes compared to the 4 minutes of the rapid field of view. And as you can see in this picture here, the PUNCH integrated field of view will allow us to see a lot more than what we currently see right now with existing satellites that we have. So here's another image that demonstrates what PUNCH will be able to do. So As you can see in this yellow rectangle, this is the field of view of Punch, and it ranges from what we would call the young solar wind, which is the middle of the corona, to almost 1 AU. And this will allow us to answer these questions that we've had for a long time that Punch will be able to answer. And they are generally, we see a textural shift from the solar corona into the inner heliosphere. And we are currently wondering, is this caused by instruments, or is this just fundamental in how the solar wind propagates throughout distance? And Punch will also be able to help us answer the question, is the solar corona structures and the solar wind structures that we see, how are they linked and how much are they correlated with each other? So hopefully Punch will answer these two major questions that we've had for a very long time because of its such large field of view, where it will be able to look at this entire region with one instrument. So as a prototype for Punch, we have this new thing called the Stereo Core 2 Deep Exposure Campaign as a prototype for Punch. These slides I'm going to be showing to you are made by Valmir at Catholic University. So I just want to say thank you to Valmir because these slides are amazing and I really am glad I'm able to present them to you guys. So first we need to talk about the data during this campaign. It was taken over 3 days between April 14th to April 16th in 2014, and it uses the Stereo Core 2 chronograph. So the normal operating for the Core 2 is 6 seconds exposures every 20 minutes. But during these 3 days, they did something special where it was 36 second exposures every 5 minutes over 72 hours, which made a total of 861 images. So when the data comes out of the telescope, it's something we call as level 1 data, where the only thing that has been done to it is the Secchi prep software, which just makes it a little bit cleaner and nicer to work with. But as you can see in this image, there's not a lot that you can tell. It just looks like a orange kind of thing. There's no detail in the corona or solar wind that you can see currently because of how long the exposure was. So to be able to get data that is useful to understanding the solar wind and the corona, we have to go to something called the level 2 data. Now the level 2 data has its background subtracted, and this allows us to see much more detail structured inside of the solar wind and the corona. But because of how the subtraction works, it still keeps things that last longer than 3 days. So coronal holes, streamers, those things. And we can also use it to assess absolute brightness because of how the data is being currently processed. Now, after we have it in the level 2 data format, we then convert it to level 3 data. And what we do here is we take it from a Cartesian plane and then we unravel it into polar coordinates. What this does for us is it allows us to see how the solar wind propagates away from the sun much easier than it is in the previous image. So as you can see here, we can see how on the y-axis it's radius. So we can see how much easier it is to look at this image and see how the solar wind changes with distance. So what I was doing this summer was porting the deep exposure campaign code, which was written in a language called PDL, into Python. Now, Perl data language is a fairly unknown language that is built on top of Perl, the normal programming language. So what Perl data language is built for is it's an extremely powerful array-oriented numerical language. And what that means is instead of using something like IDL or MATLAB, you could use Perl data language instead, as it is a free alternative compared to IDL and MATLAB, which are expensive to use if you do not have somewhere to get one of the license from. So, but you probably have never heard of Perl data language, even though it's free and IDL is expensive, really, if you're not able to get a license. And that's mainly because it lacks support from the broader data science and heliophysics community because Python took over. And that's just because I mean, we've seen how much Python is now a part of everyday life inside of the data science and just science community in general. So Perl data language and Perl in general has been kind of left behind in the shadows. But so one of the biggest problems I have run into over the summer is something I would call the branching code problem, where there is a function or a file called the level, let's call it the level code, which is taking the data from level 1 to level 2. So I have level 1 to level 1.5 file here. And inside of that, there will be a function called core rotation. And inside of core rotation, there will be a function called t-radial. So because of how these files are written, it's very built into PDL. So there's a lot of functions that exist only in PDL and have no equivalent in Python. So it's very hard to port over a single file because that file will use a lot of other PDL functions and files. So it's very difficult just to do one thing. You have to port over all these other smaller functions that need to be brought along with it. So the biggest thing I needed to port over from PDL is this library called PDL transform. And now what PDL transform does is it's a convenient way to represent coordinate transforms and resample images. There's two major functions or methods in PDL transform that I had to bring over. The apply method, which transforms vectors into the new coordinate system, and then the map method, which returns a remapped, resampled image on the new coordinate system. So inside of PDL transform, there are two types of transforms that are used. There's linear transforms, which are your normal, what you would think of linear transform, either matrices, offsets, so shifting images left and right, or rotation matrices are also here. So what you can see in these two images are the original image of a sun, and then I applied a linear 30-degree rotation matrix, which now you can see how it's rotated it downwards towards the x-axis. And if you wanted it to return to the original image, the inverse of all these linear transforms are auto-generated from it. So you can return back to the original image very easily just by calling the inverse function. So the second major transform inside of PDL transpose is t-radial. T-radial is a conversion between Cartesian coordinates to radial/polar coordinates. So what this does is it takes an image from, let's say, the sun in this case, and then we can see here how it takes it and then it changes it from XY to theta R. And that allows us to be able to do what we saw between the level 2 and then the level 3 code, where we take the image of the sun and unravel it to a single flat image, allowing us to see how the solar wind propagates. So, and here is an example of the working version in Python, where we take an image of the sun and then we can unravel it to be able to see how the solar wind propagates. So, and then there's the final and probably almost the most important transform, which is a composing transform. And what that allows us to do is take any number of linear or radial transforms and compose them into a singular large transform. So what that means is you can take 5 linear transforms and they all do different things and make one huge transform. And that's really nice and doesn't exist in Python currently, and why PDL transforms is such a great way to represent coordinate transforms, because you can do much more and have much more freedom than that currently exists in Python. So what we're looking at here is a t-radial transform that I composed with a linear transform, which allowed me to zoom in onto the bottom left-hand corner of it so I can see the more finer details in the solar wind without having to look at the entire image. So another thing I also built in Python is a testing environment for this PDL transform library, because it's always very annoying when you're using a library and it actually isn't your fault that the code isn't working, it's the library itself. So what this file does is it tests your PDL transform so that it makes sure that all the results it's producing are what they should be. So you know if you need to go and either go onto the GitHub and ask, say, why is this not working? So the conclusion and future works for this project is to finish and porting over PDL transform, which is almost done, except for one tiny little thing. And we have also laid the groundwork for porting over the rest of the stereo Core 2 deep exposure campaign code. So the biggest thing that needs to be implemented next is the auto scaling feature in map in PDL transform, as that makes it much more user-friendly than is currently available, because you have to do all the scaling right now manually. So, and then hopefully once PDL transform is complete, we will try to get implemented into SunPy or AstroPy, because it is such a powerful library for transforming images and just vector data. And it's very important to notice that all of this code is open source and available on my GitHub. So everyone is welcome to come and contribute to this project if you so desire, because it's completely open source, and the original PDL transform and just the PDL in general is a decade-long project. So there's been tons of stuff that still hasn't been ported over to the Python version. That would be great if people wanted it in Python to exist. So I just want to say thank you, and if there's any questions, I'll be free to answer them.
All right, good job. Very nice. And then you hypnotize us with the
yes,
this image, right?
The ISR on. That's the level 8 code that I don't touch. I just love the image.
Right. So are there any questions? I guess while people are thinking of their question, I'll ask mine. So you said that you create that mosaic of the outer regions essentially every 32 minutes. And you said that was from the orbital period. Is that that's? Mm-hmm.
Oh, go ahead.
So I'm just trying to visualize that. Is that the spacecraft going around the Earth, or is it actually just the rotation of the spacecraft?
I'm pretty sure it's the rotate. I'm not super this could be wrong, and I'm sure my mentor Craig could hop in and correct me, but I'm pretty sure it's when it goes around the Earth, it has a rotation effect to it that allows us to get a new image.
Okay. Is it in like a is it going to be in a sun synchronous orbit, so there's never a time where it's blocked by the Earth?
I am not sure about that.
Okay. All right. That's
yeah. Fine. Here's some more. This is some stuff I didn't present just because it's not super relevant, but
right.
Here's you can see how it makes the mosaic from, this is the level, this is a different level than the ones I were talking about, but it takes the 3 images and then it patches them together like this to make a mosaic. And then it also adds the additional ones over here. So yeah, so this is how it creates the mosaic.
Okay. All right. That sounds like plenty of detail. Someone on YouTube loves Punch and likes Lasco.
Dude, Punch is amazing, and it's a great name. It's a wonderful name.
I have a question.
Yes,
Kevin Reedy. I think I know the answer. I think does the PDL transforms today conserve flux in the images, and will the Python transforms do the same?
I do not want to give a solid yes on that because I am not 100% sure. But yeah, I feel like I wouldn't feel comfortable giving you a yes because I could be wrong.
Yeah. Okay.
That's a reasonable answer. Okay. Well then, let's thank Jake again. Good job.
Thank you.
And Megan can get set up. And meanwhile, everybody else can fill out the evaluation form.
Yeah, I'll give everybody a few minutes. I'll put the laser pointer on too, because there's a few things that I want to show too.
Mm. You're just trying to get the cats to play with the screen.
Absolutely.
All right. Okay, well, why don't we go ahead and get started? So our next talk is from Megan Conley from Morehead State University, and she's going to tell us about Whistler mode waves.
All right, so I'll take the floor now. So I am Megan, as Marty said, and I'm a rising senior at Morehead State studying astrophysics, and I'm a research intern in this case for LASP. And currently the project I've been engaging with for the past few months concerns Whistler mode waves observed during reconnection in the Earth's turbulent magnetic sheath. And I know that's a mouthful. So I'll start by breaking down like some of the concepts and like some better visualizations of the work I conducted. And it's something I'm really excited about sharing with you guys today. So let's start off by asking what is reconnection, and I'll let that GIF play out a little bit because it serves as a really good example. And okay, the answer to that is that reconnection occurs when two oppositely directed conductive plasmas magnetic fields meet at a point and then they break. And due to the nature of reconnection, the fields will merge and tear in an X-shaped geometry, so they're basically meeting in an X field. And it leads to jetting of plasma. And it brings me on to my other point that it can convert stored magnetic energy into kinetic energy and heat that can be observed. So our next question. What is the importance of magnetic reconnection? Probably the most important part. So the answer to that is the importance of reconnection stems from different points, and it really depends on what you're looking for. So the first point I pointed out was understanding the implications of plasma's behavior and physical processes that come with it. So basically, plasma is our fourth state of matter, which is basically just ionized gas in space, and it usually acts as our outlet in magnetic reconnection and has very far-reaching influences in terms of interplanetary space. As well as, this is a very universal plasma physics process that's very renowned. And usually, like, we can see examples of reconnection happening in nuclear fusion, which is something that we should probably investigate a little bit more. And another point I wanted to add too is that plasma is composes about 99.9% of the universe, while Earth, in comparison, is composed of mostly baryonic matter, which is just ordinary matter. So, in other words, reconnection acts as a stepping stone when it comes to mapping out the universe and coming to a greater understanding of how these events operate. So my next question is, where does this take place exactly? So basically, when we were talking about Earth's magnetic fields, we start to generalize it by saying the magnetosphere, which is basically all these regions working together. So starting out, we can start with solar wind, which is basically a stream of charged particles that eject from the sun and out into interplanetary space. So the solar wind is always encountering the Earth's magnetosphere in this case. And moving on a little bit more, we can talk about the bow shock, which is just the outermost layer of the magnetosphere, and it slows down any like solar wind flow coming in. And moving on a little bit more too, we go into the magnetopause, which is a boundary layer between the magnetosheath and the Earth's magnetic fields. And I know I realized that I skipped over magnetosheath, but I did that on purpose. So basically, the magnetosheath is just this region of like shock solar wind that flows around the Earth's magnetosphere. And it remains our subject of interest today. So, as promised, I zoomed in a little bit on our area of interest, and you can see like it's very turbulent looking in this orange field and such. So basically, that's turbulence happening. And the little swirls and stuff that you see is what we describe as an eddy, which is just a fluid dynamics concept where streams become intertwined with another and they swirl about basically. So I'm going to zoom in one more time into the area of turbulence and explain some things. Okay. So basically, when we're talking about turbulence, we're basically talking about changes in pressure in the plasma region. And when we talk about plasma in this region, we usually like to call it as quasi-neutral on a big scale, but when it goes to a smaller scale, you like to call it the plasma highly conductive. So as you can see, like from this GIF playing out, you can see the eddies kind of collide with each other. Well, that's a very important concept because eddies tend to break up and kind of randomly cascade to smaller scales, and energy tends to become dissipated in this case. And the heating that occurs after this loss of energy is due to turbulence. But I'll point out the most important factor too is the little flashes that are occurring. And in that case, that's reconnection happening from all these collisions occurring. So let's take a step back a little bit. So the next slide is explaining this layer called the reconnection layer. So it's like basically zooming into the magnetosheath. And I'll let the GIF play out a little bit. I know it's happening really fast, but that's kind of the point of magnetic reconnection, is that it's so fast. But in terms of how we navigate this region, a typical XYZ coordinate system doesn't tend to work. So we like to confine it into this coordinate system called LMN. And basically breaking down LMN is that like the L stands for our x-axis in this case. And the L is remains anti-parallel to the movement of the reconnection events. And it's where the geometry meets, like I was stating earlier. And as for M, that's basically our out of plane field occurring, and that's like our Z direction. So basically this is running around the axis of current in the reconnection layer. So it's either coming out or going away from you. So, and our next point is with the N coordinate system, that is dealing with the y-axis. And I just put this visualization on the right here just to counteract that craziness over here. And it's just showing the region like a little bit more in depth. So as a start, the region of focuses that I'm looking into is the ion and electron diffusion region. And we usually like to call it IDR, EDR. So basically when we're talking about those regions, the particles are decoupled while like the other respective one is basically stuck in a frozen state. So if you were talking about the electron diffusion region or something like that, like the electrons are moving, but the ions are not. So moving on a little bit more, the ion and jet and the electron jets are highly accelerated exhaust of particles. So many particles in this case are being shot out as a result of all this force occurring. And moving on a little bit more, the IMF, which is just inflowing magnetic field lines, is describing the concepts of how magnetic fields work in a closed system, basically. And our final one is the separatrix, which is just boundaries in the reconnection layer that are a result of all this colliding happening with the field lines. So into a little bit more of the scientific theory behind all this, reconnection is something we concern ourselves with the diffusion region that I explained earlier. So we like to use this theory called Ohm's law, which is just this basic EM theory that is telling us about how frozen the magnetic field is into the plasma. And when we're considering an idealized scenario, we want to consider it perfect, but we know in the magnetosheath that's not the case because it's deviating from the frozen field of plasma, which is basically just describing magnetic fields are no longer applying with plasma. So we move on a little bit to the right, like right here. We're talking about resistivity, which can explain diffusion of magnetic fields, but also in this case, it's kind of negligible because plasma is so low density in this case. So we move on to generalized theory of Ohm's law, and that takes into account our resistivity, our Hall effect, and electron pressure and inertial pressure. So breaking it down, the Hall effect is basically describing an electric field that's caused by electrons and ions being decoupled. And on to the next point too. Also, like, sorry, I was going to add this region here is describing, it doesn't do any work. So it cannot like explain why heating's happening. So we move on to the electron pressure. And that's just basically describing pressure in the EDR, like inside and outside. And it can lead to breaks into frozen field theorem. And as for the last part with inertial, it's basically the direct acceleration of electrons and can also contribute to reconnection. So since we understand the regions a little bit more and the math behind it, we can hop into like some positions that we're talking about. So in relation to Earth, the terms that we like to use for position deal with like two types, the quasi-parallel shock and the quasi-perpendicular shock. So the quasi-parallel is just describing an angle of less than 45 degrees between the normal angle and the shock background, and that's displayed right here. And one important thing to know too is that like with the IMF, you can see that it's penetrating into the magnetosheath in this case, and it's causing things to be more turbulent. So that's actually a very good lab for us to utilize for reconnection and turbulence. But as for quasi-perpendicular, it's the direct opposite. So it's just more than 45 degrees between the normal angle and the shock. And you can see it's basically perpendicular to the IMF. So our next big concept is talking about Whistler waves. And Whistler waves are something that we talk about in magnetic reconnection because one of the big parts is kinetic theory. And that was just basically the right-hand side of generalized Ohm's law I showed earlier. And as a rule of thumb, we like to say that plasma tends to interact with each other, of course, and sometimes waves form as a result, like I said here. And in that same vein, the Whistler mode waves are right-handed circularly polarized electromagnetic waves. So basically that means like they tend to like resonate around the electric fields and magnetic fields in this case, and they're also very low frequency. But the most interesting tidbit is that it's not exclusive to spectra. It can make sounds too. And I don't know if you'll be able to hear this once I play it, but it has some really cool sounds. If not, I can explain the sounds. So we'll let it play for a second. Yeah, so it makes some really cool sounds. And it basically, in this case, Whistler waves are just causing disruptions in reconnection, is what we're assuming. They move forward. Oopsie. Sorry, just give me 1 second. Okay. So how do we investigate that claim? So the equipment that we use is a collection of 4 satellites known as the Magnetospheric Multiscale Mission. And basically, the constellation has 4 tetrahedral satellites that are roughly 7 kilometers apart or so. And they navigate through the area of the Earth's diffusion region. So that's what I explained with like the primary investigation. And we like to, in the case of this study, we like to utilize the burst mode, which is just a mode that shows in short bursts like most active segments occurring, and it collects like ion and electron distributions at a rate of 30 to 150 milliseconds. And that's very, very fast. And it kind of let us look into more detail with reconnection. So a little synopsis of like the instrumentation that's used for reconnection is that in the burst mode, we like to use this this instrument called Fields, which has 2 different settings basically, or 2 different modes. FGM, and that's basically magnetic field strength. And then we use EDP, which is electric field stuff. And moving a little bit further down, we deal with FPI, which is just fast plasma investigation. And it has like these 2 instruments that are called DES and DIS, which basically has like this broad data set of like electrons and ion moments, distributions, temperature, a lot of spectra. And I added in this point for SEM, SEB, and that basically just measures like the same as FGM, but just in high frequency. So when it comes to telemetry of the MMS and back down on Earth, one of the biggest assets that I used was IDL in terms of getting real-time data from MMS. So if we want to start out knowing where we are, we can look at the spectra above. I don't know if you can see my cursor, but you see this little skinny part right here, and then you see it like kind of even out. And also we can look at the VX, it kind of like drops down and then evens out again. And you can also see that with the magnetic fields and such. Well, that basically tells us that we are in the bow shock, or quasi-parallel bow shock. And the turbulence kind of confines and such like after the fact. So we, it's moving somehow. So now that we know that we're in the quasi-parallel shock, how do we find reconnection in this case? And the answer to that is we run some tests. So when it comes to events observed that bring us here today, we can run some burst summary plots. And you can see like they have very similar qualities, both of them. Like you can see this dip up here, and then you can see some spikes and such. Well, basically those components are describing from the top, like this is the magnetic field strength, and it's dipping down. And you can see like in the electron velocity, there's this big spike here, and then like on the respective one, there's like 2 spikes. So basically, this is telling us that we are approaching an electron jet just from the electron velocity, how it spikes down in the VZ direction. And in many aspects, like I said, like there's a lot of similarities, but they're actually kind of different. Like you can see in the left event that like the structure is just so much different in BZ. And that is describing an anti-parallel magnetic field, while the right is explaining a guide field. So the reason I know that it's different is because of dissipation, which is the thing on the bottom and what it's dominated by. So as you can see for the left event, it's dominated by this pink, which is the perp for dissipation, while the one on the right is dominated by parallel in the blue. So let's take it a step further. And what we're going to look into is some electron distributions in just a moment. And a big part of the findings for this research occurs in the respect in it's kind of a fairly easy concept to look at in terms of spectra and such. So what we like to use too is the FFT, which is something that Izzy actually described in her project. And an example I provided, you can see that there's like temperature fluctuations throughout. What else is there? And then you can see like in the BPSD, there's this like little spike in FCE, but in its respective counterpart, there isn't anything. So in this case, we're saying that it's indicative of Whistler waves happening because it's being measured at half FCE, which is just cyclotron frequency. And you can also see the dissipation on the bottom, what it's dominated by, like I said earlier. So let's look at the electron distributions. So on the left, you can see some polarization data occurring. And especially if you look on the second panel to the top, you can see like what I was talking about earlier with the Whistler waves, like there's a spike and then there's nothing. So when we look at the electron distributions, we can see for the latter case, that actually for both cases, you can see this beam occurring. Well, it persists throughout the whole event, actually. So that's a very interesting find. And basically like breaking down like these events too, the 03955 kind of remains isotropic in terms of electron distribution. But as for the first case, it's actually a lot different for the guide field event. And isotropic things change, like there's a stretch in the poles. You can see heating in the Y direction, and it's becoming constricted, and the beam is getting closer. So basically, when describing this, we're talking about ellipticity, and it's kind of fixated toward the right. And actually that could be indicative of Whistler mode waves because like I said before, right-handed, like Whistler mode waves are right-handed and circularly polarized. And since it's occurring so frequently throughout this event, it may be amplifying other wave modes that's not shown. And it's just a really interesting find of how disruptive Whistler mode waves can be and how they dissipate. So on to my conclusions. The major findings of this research provides the following. The heating of the plasma occurs throughout the turbulent region, and it's not just exclusive to current sheets or the events that are happening. And moving on a little bit more, the whistlers are kind of ubiquitous in this case for the turbulent region. And there's evidence of amplitude waves that we didn't have time to investigate during this, but because of the Whistler mode waves like blocking everything. And reconnection of turbulent dissipation may be a small part of the picture. And if there's anything we should be doing for future research, future events could investigate whether whistlers can disrupt reconnection. So that's all I have. And I would like to give a big thank you to everybody. And I also have a plot for questions if we're able to. I know I talked a lot.
Very nice. Is that the Whistler wave sound that the cat is making?
Yes.
Right. All right, that was great. There was one question from YouTube. So you or Rick might be able to answer. So can these waves be detected from the ground? So the question was in the context of like, amateur radio.
Okay.
So like ham radio users. Can these propagate to the ground?
That's actually a really good question, but I would probably hand that over to Rick in that case.
So whistlers were first discovered, I think it was in either World War I or II, where military radios were actually hearing this pew, pew, pew sound. They said it sounded like whistling. So yeah, they definitely can make it to the ground. They're ubiquitous in plasma. They appear everywhere.
Right. Okay. Are there? Katie asks about nuclear fusion. Does this turbulence impact nuclear energy?
That's a pretty good question too, but that's something I'm not as knowledgeable about. So if Rick has any insight, that would help too.
Yeah, I can take that one too. One of the biggest obstacles to fusion is confining plasma in order to get the fusion reaction started. And the way they confine plasma is with magnetic fields. And it turns out that you get into this instability where reconnection is constantly happening, and at least what they call sawtooth crashes. And it's one of the biggest challenges in getting controlled fusion to happen.
All right. Any other questions? So I have a question, Steve Schwartz. Yeah. Did you find any association with where the whistlers were in relation to the reconnecting fields before, after, during?
Yeah, like in terms of like looking at electron distribution, I was like able to find like all this, like that beam I was talking about. I was seeing it before and after in those cases too, but that's just a little bit of what I know.
Yeah, I mean, that's the interesting finding here is that, people think whistlers are caused by reconnection, but in this case, they seem to be ubiquitous and happen throughout the turbulent region. So they might be disrupting reconnection rather than being a consequence.
Mm-hmm.
Yeah, interesting. All right, great. Let's thank Megan again.
Thank you, guys.
All right, cool. All right, so we have another break now, and we will resume at 20 minutes past the hour. Thanks. All right, is everybody back? Many people are back. Megan's back. All right, Iris, you want to get set up?
Yeah, sounds good. Okay. Hi, everyone. I'm Iris Wong. And this summer, I've been working as an intern at the NSO with Luke Johnson and Andy Ferrayorni. And my project has been an analysis of the Daniel K. Inouye Solar Telescope Adaptive Optics Jitter Control. And so a little bit about adaptive optics. It's part of a telescope's optic system that corrects for wavefront aberration that's caused by atmospheric turbulence. And turbulence is generated by temperature differences in the atmospheric air. So when incoming wavefronts, like this one here with parallel light rays pass through a turbulent cell of air, the light rays get distorted and cause the image to be blurred out. And so by including adaptive optics or AO into a telescope system, we can increase image resolution and allow a telescope to be diffraction limited instead of seeing limited. And so specifically for DKIST, since it's currently the world's largest solar telescope, it needs really high resolution optics to observe the solar surface and the outer atmosphere of the sun on small scales so that we can understand the dynamics of the sun better. And so the turbulence that my project is concerned with is called jitter, which is first order linear atmospheric turbulence. And this is characterized by the image shifting around in the image plane throughout an exposure, as you can see in this animation from the Lick Observatory. So instead of light rays focusing in the center of the image plane, which is indicated by the red dash, light waves that suffer from jitter end up focusing the image somewhere else in the image plane. And so throughout an exposure, that causes the image to be destabilized. And so in order to get high resolution science images to study, we need to have high image stability. And if jitter ends up being greater than the telescope's resolution, then we end up not taking a full advantage of the power of DKIST. And so this is a visualization of how adaptive works within a telescope system. First, the adaptive mirror corrects the incoming distorted wavefront and sends that light toward a beam splitter. Most of the light from the telescope ends up going to cameras or other science instruments. And then some of it is sent to a wavefront sensor, which is connected to the control system. And the wavefront sensor will measure how much of the wavefront the mirror failed to correct in that first cycle. And then the control system uses that measurement to update the commands to the adaptive mirror for the next cycle of incoming light. And so this is a look at the DKIST optical path and its adaptive optics system. So DKIST uses two active mirrors to correct wavefront aberration. And the first one is M5, which is the tip tilt mirror. And so this is just a flat mirror that corrects jitter and the first order corrections only. So it only moves in two directions, X and Y. And then the second mirror we have is M10, which is a deformable mirror. And that uses 1600 actuators that are controlled to match the higher order wavefront aberrations. And then once all the light passes through the optics, it's passed down to the Coudet lab, which houses all the science instruments and also the wavefront correction sensor. And so the wavefront correction sensor is the instrument that measures the residual wavefront that wasn't corrected by the mirrors. And then the DKIST AO control system will use the measurements from the wavefront correction sensor to update the commands to M5 and M10 for the next cycle of correction. And so this whole process runs at 2 kilohertz for DKIST, so it's a really fast and constant process. And so the main goals of my project were split into 2 parts. The first one is to analyze the performance of the jitter control for the DKIST adaptive optics system. And we did this by verifying the jitter that's seen in the control loop with the jitter that's seen in the images. And then the second part of my project was to determine the sources that are causing excess jitter in the control loop. And we did this by analyzing telemetry data of mirror commands and by comparing the performance of a MATLAB model of the control loop to the performance of the actual DKIST system. And so the first part of my project is the jitter analysis, which was basically just quantifying the jitter that we saw in these images. And so, as I mentioned before, jitter causes the light waves to focus in other parts of the image plane. So instead of being centered in each pixel, we get displaced images. And so we can characterize the shift between the displaced dot and the centered dot as a translation vector between the images. And then the X and Y components of that translation vector are the jitter values that we record. And so in signal processing, we use a technique called image cross-correlation, which helps us to determine how different a sample image is from the reference image. So looking at these two sunspot images, we measured the sample relative to the reference to see how much it had shifted. And the grayscale plot in between the two sunspot images shows a visualization of the cross-correlation array between the two. And so the peak of this cross-correlation array, or where it is the brightest, is where the images differ the most. And so the red arrow is representative of the translation vector between these two images and is pointing to the location where the images differed the most. And so by doing this calculation with a series of images throughout an exposure, we can see how the jitter value changes throughout the exposure, and taking the standard deviation of the jitter values that we calculate, we can use that as a characteristic value to compare to our goal of having less than 20 milliarcseconds of jitter for DKIST, and quantify how well the DKIST AO control loop is minimizing the jitter from the atmosphere. And so this is a look at some of the data that we analyzed. So on the left, we have a time series plot of the jitter values for this exposure from December 11th. And on the right are the corresponding images for this exposure. And so from this data set, we can see that we have really stable AO lock. We have a really high contrast image with high image stability as well. And we don't see any obvious jumps in the jitter time series plot or any sudden shifts in the images. And so that gives us relatively low standard deviation jitter values with 41 and 37 milliarcseconds for X and Y. In contrast, this other data set that we looked at, which is showing sunspot images from January, sorry, we see that the AO lock is pretty stable up until around 150 seconds, where there's an abrupt jump in the jitter values, and the animation on the right is showing a few image sequences, like right around 150 seconds. And so that jump in the jitter values indicates that the AO control loop was coming unlocked at that time. And this is, we think, most likely due to just like a large gust of turbulence or like strong winds at that time, because we can see that the AO unlocks and then locks back on immediately after. And so that sudden unlocking skewed our jitter values for this data set to be 105 and 177 milliarcseconds. But we can see that otherwise the AO lock is pretty stable for this exposure. And so our main results from this part of this jitter analysis for the images was that overall the jitter control loop is really stable when it's locked, and it doesn't just come unlocked for no reasons. Like in the sunspot image, turbulence caused the AO system to come unlocked, but then it was able to lock stably back up again. And so when it does come unlocked, we see the corresponding spikes in the jitter values and can confirm that the images are shifting around with that extra jitter. And in general, our calculated jitter values were between 30 and 60 milliarcseconds. And so that means that the jitter control system isn't matching our performance needs of having less than 20 milliarcseconds of jitter yet. And so we still need to investigate where that extra jitter is coming from. And so that brings me to the next part of my analysis, which was analyzing telemetry data from the jitter correction control loop. And so the telemetry data is looking at commands that are sent to and from the tip tilt mirror. And so we can see the response of the adaptive optic system and the tip tilt mirror as the control system is running the correction. And so the two components of the telemetry data that I analyzed are actuator commands, which are the commands that are sent from the wavefront sensor to the tip tilt mirror to correct the incoming wavefront. And then the second part of the telemetry data are the residual error shifts of the mirror. So this is the part of the atmosphere that the mirrors don't correct in a given cycle. And then that residual error is fed back to the wavefront sensor to create the next set of actuator commands for the tip tilt mirror. And so the two types of telemetry data that I looked at were closed loop data, which is taken when the system is actively correcting the jitter.
So closed loop data includes both actuator commands and the residual error shifts while the control loop is correcting jitter. And then also open loop data sets were taken when the system wasn't actively correcting the jitter. So no actuator commands are being sent to the tip tilt mirror, and we're just saving the residual shifts of the mirror as it's reacting to the turbulence from the atmosphere. And so by looking at power spectra of this time series data, we can see how strong the jitter is from the telemetry data at different frequencies. And from our initial analysis, we saw that in this telemetry data, our average jitter values were between 30 and 60 milliarc seconds, which matches what we saw in the image jitter analysis earlier. And so the first step of this telemetry analysis was to quantify how much of the jitter in the residual shift spectra was due to non-atmospheric effects. And so we made sure that the peaks we were looking at weren't a product of noise in the spectra by using a Welch method for power spectral density estimation to average out the noise in the spectrum. And then we subtracted the effect of the atmosphere by approximating the atmosphere with a median filter, which is shown in this upper right-hand plot, where the red curve is the median filter that we approximated as the atmosphere, and then subtracted that from the total spectrum to just get non-atmospheric contributions. And so we were able to identify the contribution of non-atmospheric jitter peaks, and of the 30 and 60 milliarc seconds of total jitter that we originally found, around 75% of that jitter came from non-atmospheric peaks. And so the peaks that I've highlighted on the left here in this residual shift spectrum all contributed more than 5 milliarc seconds of jitter, and they were all consistently seen across multiple data sets. And so these are obviously a really big contribution, but we haven't been able to identify the sources of the peaks yet, but we definitely have some guesses and ideas. So for example, the 33 and 40 hertz ones we think are from vibrations of the Coude platform at the telescope. The 102 hertz one we think is from fans that are mounted on the wavefront sensor camera. And then the 250 hertz one we think is caused by electronic interference from the camera readout noise. And so once we were able to quantify how much non-atmospheric jitter we were getting, we took a look at the system as a whole to assess the performance. And so this is a look at our AO system feedback control loop and see the signal flow from each component. So the tip tilt mirror, which is M5, corrects the incoming atmospheric turbulence, which is the input signal. And then from there, we get the residual error, which is the atmospheric turbulence minus the position of the mirror. And then that residual error is sent to the wavefront sensor, and the wavefront sensor will reconstruct the distorted wavefront from the atmosphere and send that measurement to the microcontroller. And then the microcontroller is responsible for converting the sensor measurement to actuator commands for the mirror. And it relies on a gain value to determine the percentage of error that is corrected in each cycle. And so for our system, we have 2 different gain values that can determine that system. So for the proportional response, the system multiplies the incoming residual error signal by a constant proportional gain value. And then for the integral response, the system averages the incoming residual error signal over time and then multiplies that average value by an integral gain value. And then so the microcontroller adds these 2 responses together and sends them as an actuator command to the tip tilt mirror. And then the tip tilt mirror can continue to correct jitter. And so the way that we can assess our system's performance is through the use of transfer functions, and transfer functions represent the frequency dependence of the system's correction response. And so this is calculated by dividing the residual error by the input signal. And so having a low transfer function value less than 1 means that we have a good correction. When it equals 1, it means that the residual error and the input signal are the same, so no correction is happening. And then when the transfer function is greater than 1, that means we're actually amplifying the jitter from the input signal. And so from the top plot, we can see that the residual error, which is the red curve, divided by the input signals, which is the black curve, can give us transfer functions that resemble the plot below it. And so this plot shows the variation of different transfer function shapes we can get based on how we vary our integral gain value in our control loop. And so as you increase the integral gain value,
the correction at low frequencies gets better. So as we move from the red to the orange to the blue curve, the value gets lower at lower frequencies, but then we end up amplifying the jitter a bit more at the higher frequencies. So it's a bit of a trade-off with our gain value. And so this data is from simulated atmospheric data. So this just shows like an ideal transfer function shape. And so in order to calculate transfer functions for our own system using real telemetry data, we actually needed to create our own input signal from the telemetry data that we have. Since although we have open loop telemetry data, which can characterize the uncorrected atmosphere, it can get saturated and we didn't really have enough consistent data sets to work with. And so by using closed loop data, we were able to construct these pseudo open loops to approximate the atmosphere. And so closed loop data, as I mentioned before, contains actuator commands, which are the atmospheric jitter that was corrected by the system, as well as residual tilt shifts of the mirror, which are the atmospheric jitter that was not corrected by the mirrors. And so by adding these two together, we can get an approximation for the total uncorrected atmosphere. And so in this plot below, you can see that the pseudo open loop matches our open loop spectra pretty well. And so this is a look at our system transfer functions for DKIST, and each line shows a different data set, so different days of observing and also different parameters of the control loop. And so we can see that the range of shapes matches what we saw earlier with the simulated data sets. And so this confirms that our system is running as expected for a proportional integral control loop. So we can compare these plots with this plot from earlier. And so now that we have a sense of what the DKIST system performance is like, we tried to modify the gain values in our MATLAB model of our system to match the model transfer function to the DKIST system transfer function. And so in this top plot, we were able to see that comparison between the residual error spectra from DKIST, which is in red, and also the residual error spectra from the model, which is in blue. And then below that, we see a comparison of their transfer functions for the same input data. And so from these comparisons, we can see that they match really well. And so we know that the modeled system is working as expected and is able to match our DKIST system really well. And so by studying the model's response to different inputs, that can give us a sense of how we can improve the actual DKIST system. And so the different inputs we put into the model were on-sky pseudo open loop data that I calculated, on-sky open loop data, as well as lab open loop data, which is where we used a heat gun to simulate atmospheric turbulence in the lab. And then we also have theoretical atmospheric windshake data, which is developed from turbulence theory. And so on the left here, we can see the spectra of those input data sets. And then on the right, we have the residual error spectra that we got from the model. And so our main takeaways from the model's response to these different inputs is that first, we've confirmed that the pseudo open loop is a good approximation for our open loop data and for the uncorrected atmosphere based on how closely the red and the blue lines match, which are the pseudo open loop and the open loop. And then secondly, we know that our theoretical atmospheric data, which is the orange line, underestimates the mid and high frequency jitter, since we can see that the orange line is well below both the lab data, which is in gray, and also the on-sky data, which is red and blue. And the fact that there was high frequency jitter in these spectra meant that we had to run our model with higher proportional gain than before to get the system response, to get the model response to match the system response. And then lastly, we see that there are some peaks like the one at 80 Hertz. So in the input signal, you can see here at 80 Hertz, and then also in the residual error at 80 Hertz. We only see that peak in the on-sky data and not in the lab data, which is the gray curve. And so these peaks that only show up in the on-sky data can only be explained by vibrations in the telescope structure. So we know that that's contributing some excess jitter. And so our main conclusions from this analysis project are that the DKIST jitter control system is performing well at low frequencies. And so that the system was designed to mitigate low frequency jitter, since we knew that that would be where the atmosphere is the strongest. So it's a nice confirmation that our system is working as we would like it to at those frequencies. But because there is unanticipated excess jitter in the 40 and 150 hertz range, it's causing worse performance there. And we know that some of the extra jitter peaks in that range are caused by telescopic vibrations, but we still need to investigate the different sources that are contributing to the other strong peaks. And so the next steps for this project will be to have an engineering campaign at DKIST where we can isolate different systems in the AO and in the telescope to verify the sources of the strong jitter peaks that we've seen that aren't caused by the atmosphere. And then once we can identify the components that are responsible for the jitter, we can then implement jitter reduction measures such as vibration isolation padding. And then eventually we'll have to also update and improve our control algorithm for the system so that its response at middle frequencies can get better. And so thank you. And I'd be happy to answer any questions that you have.
All right, great job. Are there questions? So I have hopefully an easy question, right? So you're updating 1600 actuators at 2 kilohertz. Is that a big burden for the computing processing to figure out what signals to send, or is that I don't know how awesome modern computers are. So is that a big deal or not?
I think for the deformable mirror, it's definitely like a lot of actuators, but for the tip tilt mirror, which is the one that I was mostly working with, we actually only have 2 actuators that move in the X and Y direction. So it's like much easier for that. But yeah, I think it's, yeah.
All right, other questions? So this is not the only telescope that uses adaptive optics. Is it significantly higher performance than say other astronomical telescopes, or do you know?
I'm not sure, but I do know that for like solar astronomy, the adaptive optics is a bit different. Just because, yeah, the difference between nighttime and daytime astronomy is like, there's definitely
it's
more.
It's like night and day.
Yeah, yeah. There's more turbulence during the day, so there are different considerations there. But I think just because like DKIST is the largest solar telescope right now, its adaptive optics system is a bit more robust than the other ones. But yeah, I'm not sure about details.
Okay, that sounds great. Okay, I don't see any other questions, so let's thank Iris again.
Thank you.
All right, and everybody should fill out their evaluations for Iris, and then meanwhile, Eden can get set up with the screen sharing. Okay, our next talk is Eden Ashibo from Metro State, who's going to talk about polarization. All right, start whenever you're ready. You are still muted. Yes, now we can hear you. All right. So hello, everyone. I will start my talk by introducing my mentor, myself, and our research topic.
My mentor is Dimitri. He is a research scientist at Laboratory for Atmospheric and Space Physics at CU Boulder, and I am a senior year student at MSU Denver, majoring aerospace science. And our research topic is polarization of candidate post-AGB stars. So in the next slide, in the introduction part, I will talk about how this research went through and what we did for this research. So for the introduction part, the scientific goal of this research is to study the physical property of post-AGB star phase of the observed stars or objects. We mainly focused on the transition phase from red giant star to planetary nebula. Actually, the red giant star image is just an illustration. In reality, it looks like this little dot. When it starts to get to the other phase, so the red giant star structure starts to expand and widen by creating different structure around its core. And we used a polarization to study different physical property of the star structure in this specific phase. This polarization helped us to analyze or to study the property of the star. And that in that phase. And the reason why we're interested in this specific stage is because in life cycle of low mass star, this post-AGB phase takes like the shortest period. It is about 10 to 20,000 years. So it is not easy to access and to study this phase. So that's one of our interest to study this transition phase. So as I said, we use polarization of object to study the property of the observed objects. So polarization by itself is a property of light that can be used to study the geometry of objects, even when spatial information is not available. So in our study, and as I showed in the previous slide, we don't know what's going on that transition phase, that particular transition phase. So this polarization technique tell us information about the shape in the property and about the structure of those stars. So this image shows us just general explanation of how polarization takes place. For example, this is our light source, and this is the light emitted from this source that oscillated in random direction, perpendicular to its propagation wave. And if we use a device that can polarize this randomly distributed light, then that light can be transformed to the other light that we can call it polarized light. So as I said, polarization is a property of light when the light emitted from its source and when it interacts with a surface. So it polarized in terms of the orientation of that surface. So when we use a vertical orientation or a vertical device, so it filters only vertically oriented light. So after it filtered, it will orient this light in a single plane that the light oscillates vertically. So we can say this one vertically polarized light, and this one is a polarizer, and this one is a light beam or unpolarized light. So the same concept will work in our device, the one that observe the light that emitted from the stars or from the astronomical object. So polarization is a property of light. So when the light emitted from its source and when it interacts with any object or any atmosphere, then it reflected and it will orient or it will polarize in orientation of the same shape with the surface that it interacted with. For example, this surface is horizontal surface, and the light that emitted from the source, when it interact or when it hit the surface, it reflected in this point, and then this light polarized horizontally because the surface is horizontal. But here, unpolarized lights, this unpolarized light has a randomly distributed magnetic field. When it polarized, it only hold a shape or state in terms of the surface that it interacted with. So when the light emitted from the stars and they pass through a different atmosphere, and that light will interact with a particle or other dusty particle through in the atmosphere, and the light that came from the source, it is initially unpolarized, but when it passed through different atmosphere, it may polarize partially or it may polarize fully in some extent. And also when it interacts with dusty particle, it also polarized in some extent. So the reason why we use polarization using a special device, so to measure how the coming light polarized, or if it is polarized, we will know the state of polarization, and if the light that is emitted from the source were not polarized, so we can easily polarize by using a device that I will talk in our method. So this is part of our device that can detect or that can polarize the light that came from the source. The picture on the left side is a filter color that we used, and we used like green, blue, and red filter to cover our camera, and the light that came from the outside environment that passed through this filter and this device by the right side will detect that photon that passed through different color filters, and then that will polarize the lights based on their orientation. For example, this micro polarizer has a horizontal orientation or 0 degree, and this one has 45 or positive 45 degree, and this one is negative 45 or diagonal diagonal orientation of the micro polarizer, and this one is vertical orientation or 90 degree orientation of the micro polarizer. So this is a micro polarizer that is located in our camera. When So I will explain it by showing this telescope. So this is a telescope that can collect or observe the outside light, the light that came from the source. And after it collected the light, that collected light go to the camera by passing through different color filter based on the color that we used when we observe a certain object. So this is the telescope, and this part is this little object attached to the bottom of the telescope is the camera, and this rectangular object is the thing to place our filter to cover our camera, and then the light or the radiation that collected by the telescope passed through this object that was covered by a different filter, and after it getting to this camera, I'm sorry. I'm sorry. Yeah, so this is our camera that our micro polarizer is deployed into it. Then when the collected light reach to the micro polarizer, that micro polarizer detect that light and orient based on the orientation that the micro polarizer design. As I showed you, there are four kinds of orientation on the micropolarizer, in 45 degree, negative 45 degree in, 0 degree and 90 degree. So this is how this telescope helped us to observe the stars. So for our method, we also used one of our object, which is hand polarized object, HD 90156. So we used this object for calibration source, and this object we used to characterize the instrument's performance. When I say instrument performance, how this object characterize the instrument performance, because we already knew as this object is hand polarized, and this plot shows us the analyzed result of this object data. That means, as I said, when the light came from outside, then the micropolarizer detect and orient those intensity in different orientation. So here I have like in this plot, in the first plot, Q is the mean value orientation of the difference between 0 degree and 90 degree orientation, and the U or the blue line or this part is the mean value of U. That means the orientation difference between negative 45 and 45. So this object is hand polarized, but still there is some value. So I want to say something about polarization. To say an object is unpolarized, the value of U, the Q and U value should fall at 0. And I said this object is unpolarized, but still there is some value here. So that can tell us if there is some error in the measurement. So we use this object as a calibration source to subtract the errors from the other object when we analyze the other stars. And as an example, I used here HD 78344 star that taken by blue filter. And this is the final result of this object after the raw image is processed through MATLAB coding. So I will talk about the MATLAB coding in the next slide. So here I use this image to show how we identify if the object is polarized or unpolarized. As we see, the value of Q for HD 78344 star, it is getting far away from 0, and in this side it is also getting far away from 0 because when we compare the value of U for these two objects, like for the HD 9156, it is like negative 0.005 or something like that, and for this one 0.04. So it is a big number than that one. So when the value is getting far away from 0, so we can determine that object is strongly polarized. So if that object is strongly polarized, so that means we filtered the light that came from the source, and then that information or that filtered or polarized light gives her detailed information about the original object, the source. And this is also our one of our method, MATLAB coding. So we analyzed the polarization state of the object by using this code. The raw image of post-AGB star taken in blue, green, and red filters were analyzed by using MATLAB. So how we analyzed it by using median value of Q, median value of U, and this code can plot analyzed image of the data that created by our camera. And this is our observation description, that what time we observe each object and what filter we used and how many times we measured them and how long it takes when we measured them, and their air mass. Here the air mass, here the air mass is the atmosphere that the light passed through when observation took place. So for example, for object RV cool, this object was taken or observed at 10:05 with a red filter, and we measured it 10 times. Each measurement took 20 seconds. And the same as for the other objects. In our result part, after we processed the raw data through MATLAB coding, so we found a result for 5 stars that we analyzed. So this is this data is the final result of HD 9156 star that we used as a calibration source. The above 3 plot shows us raw data image that they were not processed through MATLAB coding, but the bottom 3 images are the processed image that we collected from our camera. So here the little star shows this, the little yellow dot is the star that we observed. And so this is just the raw data, the upper one, and the bottom three plot gives us the analyzed information of that object that taken in blue filter. So I used blue here because we used blue filter to observe this object, and we also use red filter to observe this object, and we use green to observe this object. So this plot shows us a Q and U distribution of the object. As I mentioned earlier, Q is the orientation difference between horizontal and vertical polarization, or 0 degree or 90 degree. And U is the polarization orientation difference between 45 and negative 45 degree. So, so to say an object is polarized, or if we want to say an object is hand polarized, the value of Q and U, the mean value of Q and U needs to fall at 0 or very close to 0. So for HD 9156, we already know as it is hand polarized, but still there is some value very close to 0. So we can assume it as an error to subtract from the other object that we polarized. Okay, this one is a result of our AR pure star, and as I said in the previous slide, the above three images are raw image data, and the bottom three are the analyzed data of that object. So as I said before, this the Q and U value of this object at the bottom plot shows us like it is getting far away from the values. The mean value is getting far away from 0, and we can say this object is relatively has a strong polarization. And so we use different filter, blue, red, and green. So, I mean, they all have the same information. I mean, like when we use a red filter, then the mean value of Q, the mean value of U fall between 0.05 and 0.04. I mean, it is still in a good polarization state. Because it is like the value is getting far away from 0, and the mean value of Q orientation also has a relatively big number than the other objects, and we also analyzed that object using green filter. So this information is the final result of HD 78344 star, and the above three is the raw image data. And in the bottom plot, we can learn how it polarized, because by seeing the value from 0, or by comparing our HD 9156 that we used as a calibration source. So this star also has a strong polarization, because when we see the value of the mean value of Q and U, it has like big value other than the other objects, and we use we used blue, green, and red filter, and this is also the same information for our HD 101584 star. And so we use error propagation formula to calculate or to know the effect of measurement of uncertainty. In this equation, Q star is the mean value of Q orientation. Q is the polarization difference between 0 degree and 90 degree, and the same as for U value. And by using this formula, we calculated the standard deviation, and that can tell us to know the effect of measurement of uncertainty. And this table is our result summary.
Can I ask how many more slides you have?
After this one, conclusion.
Okay.
Okay, yeah. This is the table representation of summary for the analyzed star. So from this, this is the object or the stars, and this is the filters. And this is the difference between the 0 degree and 90 degree orientation. And this one is the polarization difference in 45 and negative 45 degree. And the last two table is standard deviation of Q and U. So from this table, HD 78344 has a strong polarization state by seeing the value of mean value of Q and mean value of U. So that means we can get good information from that star. So in the conclusion part, I learned analyzing astronomical objects, and we identified an object with a strong polarization, and we used MATLAB coding to process the observed data. And by using error propagation, we calculate or we fixed the uncertainty of the polarization or measurement. And for this sample, the stars that have a strong polarization in our sample are good candidates for further observation in to study their phase. And this is my reference. And thank you for listening. And let me know if you have questions.
All right, thank you very much. So we're a little over time. If people want to ask their questions in the chat,
okay,
do that during the break. We'll come back in 8 minutes at 20 past. All right, thank you.
All right.
Leah, you look happy that you're about to give this presentation.
Oh yeah, I'm really excited.
That's all right. You're an old pro now.
I really am. I've done like 5 Zoom presentations.
You're a Zoom master in this case. Zoom master. Claire is the wizard of Zoom. I'm just a Zoom minion.
Takes a village and all that, you know. You get to be the face of Zoom.
Ah! Megan, what's the DGS-GADS? That's just keyboard smash, basically. Ah, okay. All right. Usually I just do that a lot, so just shows how excited I am. So
all
right, it's 20 past. If everybody's hopefully back from the break. Yep, if only Zoom had emojis. Huh? I guess it's got the like thumb up. But all right, you want to get set up to start sharing?
Sure thing. All right, I hate how this bar is always right where I want to click. All right. Got my pointer and everything.
Whoa, look at that Zoom. Okay, welcome back, everybody. We have 2 more talks today. Thanks to everybody for sticking with us. Next is Leah Kaiser from Northland College, who's going to tell us all about neutral lines. Take it away.
So welcome to the presentation. I worked with Alexi over the summer for the National Solar Observatory, and we're going to be examining some neutral line properties and their connection to flare activity. So let's get started. Wow, that would have been really dramatic if my slide had changed. All right, so I'm going to start off with a little bit of intro on space weather. By now, I'm sure we've got a pretty good understanding of what it is, but let's just go over it again just for fun. So we know that it can be kind of a destructive force. It can impact power grids, communications, GPS, satellites, aviation, a whole bunch of other industries. But kind of what is it? So on the sun, there are these active regions, and from them, we can sometimes have eruptive events, whether those are solar flares or coronal mass ejections, which are a lot more energetic. Both can end up impacting us here on Earth through X-ray fluxes that cause radio blackouts. There's energetic particles that get produced that cause solar radiation storms. And then if we've got this coronal mass ejection that's kind of facing our direction on Earth, we can actually end up with a geomagnetic storm. And that's going to be the thing that's kind of the most important that we watch out for, because it can affect, as I said, communications and GPS and all these systems that we really need now that we're kind of more focused on technology, and we really rely on those systems. So it's vital that we improve this forecasting. Right now, we know what solar events are most likely to cause the most damage, but we haven't got a great understanding of exactly what causes them and how we can best predict them. So a couple of improvements we need to make are accuracy of our forecasts. We've seen in a couple of our previous talks that they don't exactly know how strong a storm is going to be, what kind of impacts we can have on Earth. So we need to improve the accuracy, but also the timing of predicted events by increasing those warning times. If we saw in one of those talks, sometimes they've got 10 minutes of lead time, sometimes they've got several hours of lead time. So right now they use coronagraphs, they use, solar wind models, they've got electron flux monitors happening, but we still need to improve kind of that forecasting ability. So my project is going to examine connections between neutral lines and flare activity and seeing if there are relationships between those properties to develop a better understanding of flare activity. If we understand what causes flares and kind of how they form, we might be able to better predict them and improve those space forecasts that we've determined are really important to getting right. So a bit of an overview, I was using IDL this summer to examine magnetograms. So to my right, this is an example of one of the magnetograms I might have looked at. And each of these pixel values is going to correspond to a magnetic flux value, basically. And within that, we're identifying neutral lines, which is my bottom figure here. All those lines are where we've determined using IDL that a neutral line is. And a neutral line basically ends up being the border between this black and white area along these active regions. And it's where there's kind of a neutrality between the incoming and outgoing flux. So we calculated some properties of these neutral lines by each Carrington rotation. So we've got this gong data, and it's a magnetogram per Carrington rotation. So we go through, and I ended up having about 184 different maps to look at. And then on each of those, we examine the connections between the neutral line properties, magnetic flux, and flare activity. And then I ended up creating some scatter plots of the data to see the relationships. So those properties that I've been talking about, we examined the gradient values, specifically the maximum gradient. And that's what's plotted here. The very dark regions and the very light regions are where the gradient ended up being the strongest, meaning that there was the highest change in magnetic flux over a short distance. And then we also examined the neutral line length by just finding the total length of the neutral lines that are present on each magnetogram. And then I also determined a kind of strong neutral line length, and it's determined to be strong if it has a gradient value of 10 Gauss per degrees or greater along the entire length of the line. And then I also found flare index. This is kind of a simple way to measure flare activity. It's the sum of the peak flux of each flare, and then you take the total of all of those fluxes added together for each Carrington rotation. So you end up with one value per rotation that's sort of, it's a simple way of kind of measuring the activity that's occurring on the sun during that about month or so period. And I got this from the Hinode Flare Index catalog. So let's hop into these plots that I found. The first one is going to be our neutral line length. And this is over the period of about 14 years or so, which is how far the gong data went back. And we see neutral lines end up getting a little bit bigger during maximum, and then minimum, sorry. And then they end up dropping during this maximum, and they get longer again as we head towards our minimum. And our explanation for that was that during these maximum periods, there's a lot of active regions on the sun. The sunspots are becoming more complex. And as they do that, the neutral lines kind of get all mixed up and jumbled and actually end up shortening a little bit. And then if we look at our strong neutral lines, we end up seeing that these stronger lines sort of follow a similar trend. They get a little bit bigger actually though during our maximum and a little bit smaller during our minimum. And then our maximum gradient values, you would expect these obviously to be the highest during our solar maximum. And we do see that over the course of, a solar cycle, it increases and then it falls again. And this flare index follows a similar pattern. During that maximum, you get the highest flare index values. And then once I found this data, I ended up comparing it to our flare index. And what we see is there's really no relationship here. All of these lines are basically flat, the best fit line that we've added. This one is a little bit weird since it falls below our data, but it also really doesn't show that strong of a relationship. So our thinking was maybe this flux value that we end up with is kind of overriding those relationships. So the flux versus flare index ends up being a very strong relationship. We see a good trend line here. And this makes sense. The higher flux values, the higher magnetic activity you've got, you're probably going to end up with some more flare activity during those cases where the flux value is very high. So once we found this sort of primary relationship, we actually ended up removing it from our data set. And I've got this adjusted flare index, which has taken out that primary relationship. And this is to see if maybe there's some underlying relationships that we just weren't able to see. But in this case, once again, our trend lines are almost horizontal. Any little bit of a fall here really isn't statistically significant. So this basically tells us there's not really a strong relationship here. And what we're looking at is, not very strong relationship between our properties and our flare index. So I've included this little frowny cat as a nod to Marty. So we found that no relationship exists. Slight trends end up not being statistically significant. So during one solar rotation, those relationships aren't really strong enough for us to end up seeing. Flares are very short-lived, as we know sometimes, and they may not make enough of a difference in our properties for us to see it on such a broad scale. So future work might be focusing on specific active regions. As we can see here, there's 16 different regions you could be looking at on one magnetogram. So these smaller scales might end up having a stronger relationship, and you might see more of that trend line as we look at a specific active region versus the entire solar map. Another thing to look at is maybe add some more properties. We've only looked at really 3. If we look at some other ones, there might be better relationships. And then possibly using a more in-depth flare index. The one I used ended up being a very simple one, but there are many different ways to calculate the flare index. And you can certainly use a different one to see if those relationships are maybe a bit more obvious if you use a different flare index calculation. So thank you. Are there any questions?
All right, nice job. Are there any immediate questions? If not, I do have one. Can you go back to slide 8?
Yeah.
So the one in the upper left, so the neutral line length, so that is the adding up the lengths of all of the neutral lines that you found?
Yes, this would be adding all of them up. Okay.
Because you made a comment of like, well, if there's lots of active regions at solar maximum, maybe the neutral lines get shortened. And so could it also just be that it's more difficult to find them in the way you're finding them, or you think that's not an issue?
I would say we used an IDL program that already existed, a contouring program, to find them. So I'm not sure if it would end up making a difference to the program itself, but I could certainly see that maybe being the case.
Okay, because the timing is sort of correlated to the solar cycle. The solar cycle kind of started in 2012. I mean, it was strong in 2012 and went on. So either it's during the declining phase, or maybe it's just an artifact of the method.
Yeah.
Okay, thanks. Are there any other questions from the audience?
Yeah, this is Serena. I've got a question. In slide 11.
Yep.
You said you repeated your plots, eliminating exactly what?
Yeah, so we took this flux versus flare index and we actually subtracted sort of the difference between our property values and our flare index versus flux values to kind of get our flare index values if that relationship really wasn't there.
So I'm sorry, not understanding. So you took into consideration
Only the flux, or you repeat the data?
So I guess we definitely took into account this kind of flux versus flare index, and we sort of just ended up finding a difference between our properties and this relationship here. So it was the same kind of data set. We just manipulated it a little bit.
Okay. Okay. Thanks.
Yeah. So before you move away from the slide, it almost looks like there's a bunch of points down near the flare index of 0 that are really influencing that line. So maybe if you put some threshold and you said, okay, anything with a flare index less than 0.001, I won't include. And then it looks like the rest of the data kind of does fall on a line. It's not, the slope is almost 0, but not quite.
Yeah, and that was also another hard thing, is deciding kind of where to put our threshold and what points to include.
Right. One idea is, you sort of, pick a threshold, do the fit, calculate the, how good the fit is. And then, you nudge the threshold again and recalculate how good the fit is. And ideally there's some minimum value where then it's as good a fit as you're going to get.
Yeah.
Was someone else going to comment? Okay. Yeah, Christian also says, yeah, all those points down in the corner look like they're influencing the fit. Okay, great. If there's no other questions, then let's thank Leah again. Good job. All right, Rudy, you want to get set up? Yep. The final talk for today. Everybody is excited. Everybody's been looking forward to this talk all day, right? All right. Oh, yes. Sorry. People should fill out the surveys. I'm sorry that I haven't been reminding that. I can scroll up in the chat and post it again in the chat. Yep, there we go. Someone else has already. So yeah, let's give people a moment to fill out the evaluations for any that we haven't so far.
I'm sorry, I didn't know that I was on mute there for a second.
That's okay. It's just people a moment to fill out the evaluations and catch up on the schedule. Somebody may have set their alarm to check in at 2:40. So if you start at 2:39, they're like, I missed a minute. All right. Well, that's probably close enough. So our last talk for today is Rudy Parra from Central New Mexico Community College, and he's going to tell us about H-alpha. All right.
Sure. All right.
Thanks.
Thank you, Marty, for that introduction. I know that I'm the last presentation for today, so I understand that people are tired or, but I will try my best to make this as fun as possible. So let's continue. So as you heard, my name is Rudy Parra, and I spent my summer working remotely for the research institution, the National Solar Observatory, better known as the NSO. In what seemed like a short span of time, the 3 months I spent actively investigating the variability of the H-alpha line observed a high spectral resolution in the solar atmosphere throughout time. Now, we analyzed temporal variations of the properties of the H-alpha line in Sun as a star observations. The goal is to understand how magnetic, photospheric, and chromospheric features modulate the variations of the H-alpha core-to-wing ratio at the 27 days rotational timescale. Now, you may ask yourselves, what drives us to conduct such things like this? Well, that all begins with the energy that reaches to the Earth's top atmosphere called the solar irradiance. The solar irradiance varies over temporal scales, ranging from centuries to millennia, and is driven by the solar activity. Now, it's no secret that the sun has an 11-year cycle of solar activity, which manifests, for instance, in the variation of sunspots. Sunspots are dark regions of the solar disk caused by concentrated magnetic fields. The solar radiance is measured higher during solar maximum, which corresponds to periods of high sunspot numbers and magnetic activity, compared to solar minimum, where very little to no activity of sunspots occur. Now, Earth's climate results from a delicate balance between incoming solar radiation and outgoing thermal radiation. The slightest variation in these parameters is known to have a strong effect in the Earth's climate. Now, it's known that approximately 30% of the solar energy that strikes Earth is reflected back into space. Some factors do come into play, such as clouds, atmospheric aerosols, sand, ocean surfaces. They all have a huge impact in deflecting the incoming radiation rays. And of course, the other 70% is known to be absorbed by land, ocean, and the atmosphere. Now, to understand the connection between the solar radiance and the H-alpha and how the solar radiation affects the Earth, climatologists would need measurements of the solar radiance extending for long temporal scales. Unfortunately, though, measurements started in the late 70s, so they are only available for only a few decades. To extend estimates of the solar radiance to the past, we rely on models or proxies. For the people who don't know what proxies are, they are surrogates of irradiance that allow us to estimate irradiance variability at times when they were not available. Now, in this study, I did focus on analyzing the variability of properties of the H-alpha line, which could be employed to understand the variability of the solar radiation forming in the chromosphere. Specifically, I investigated how the H-alpha core-to-wing ratio is affected by the presence of the magnetic features on the solar disk. Now, to reach my goal, I had to analyze a correlation of the H-alpha core-to-wing ratio with sunspot area, filament area, and the faculae area. Here to your right, you can see a clear representation of what exactly those areas looks like on the solar disk. Everybody has seen the sunspot, faculae, and the filaments. Now, before I view the correlations between the four quantities, I first needed to select the temporal range that I believe would give me a greater result for me to analyze. In my research, I was given data from a mentor of the solar radiance spanning the decades starting from the year 2007 all the way to the year 2017. I needed to select the time in which we had a lot of sunspot areas but no filament areas, and a lot of filament areas but no sunspot areas. Doing so allowed me to look at a visual inspection of the plots to see what was affecting the most sunspots or filaments. Sorry. I found that the year 2010, specifically after the 200th day of the year, would be a perfect range to further my analysis, only to see in fact the number of filaments has any correlation with the solar radiance. Now, we have focused on observations acquired over one solar rotation between August 18th to September 15th of the year 2010. As you can see here, I have grabbed the H-alpha and the continuum solar disk images from the Solar Monitor website to view the sunspot areas in that given range. In this image, it was actually taken on August 27th of 2010. Actually, let me get my laser pointer. Okay, so here is actually a much closer image of those two sunspots found on the solar disk on that given date. you can actually see one of the sunspots here is actually at the very edge of the solar disk, but as you can tell, the instrument still registered that as a sunspot number. And here again is just like the same image, but in the continuum solar disk images. It's always nice to see them up close, isn't it? Okay, so here's another solar disk image of the H alpha in the continuum. This particular image was taken on September 13th. These sets of images mainly focus on the amount of filaments that are occurring within the specific temporal range. Now, you may ask how I was able to obtain this, the temporal range scaled results, and that is by downloading the data acquired from 3 instruments. First being is the Integrated Sunlight Spectrometer, better known as the ISS. Second is the Precision Solar Photometric Telescope, also known as the PSPT. And lastly, the Neodon Spectrohidrogram. What we did is we took this data and focused on a specific temporal range scale. Then we used IDL coding to actually put those plots up to life. Here, as you see, is a quarter ring ratio plot spanning the entire year of 2010. In the plot, you can also see the added arrow lines that I did add. Now, you may notice that there are some variations that seem out of the ordinary towards the end of the year. I want to be completely honest, we actually don't understand these set of values. These values are consistently higher than the beginning of the year. Our guess is that it could be a physical issue or an instrumental error, but for the time being, we have only focused a certain temporal range that does not have this particular spike. Now, here's the image of the quarter ring ratio in that specific temporal scale range that doesn't have that particular spike, which is taken on the 230th day all the way through the 250th day of the year. And I just want to go ahead and show you that this same scale range goes for the other plots. So this is the core to wing ratio. This is the sunspot area, filaments area, that's a data we took there. And lastly, the faculae area. As you can see in this slide, I've gathered all of the acquired plots together to gain a better visual inspection to see if there are any correlations against themselves. First, we begin the comparison of the correlation between the sunspot areas and the filament areas. You start to take notice that the values on the plot both seem like they don't correlate with each other towards the beginning of the selected range scale. Now, in the beginning of the selected temporal scale range, it's sort of obvious that there's zero similarity amongst the two, but we begin to see just at the 251 mark, approximately right around here, an increase of those values begin to formulate, not exactly aligned in accordance with each other, but we do see a slight increase of those specific variations. Now, this is the second set of plots, and it's comparing the quarter wing ratio versus the sunspot area. Now, this is actually one of the plots that I was excited to see. Once it got to analyze closer amongst the two, you can quickly see that in fact there is a substantially close correlation between the two plots. Keep note that this does support what we were trying to find in our research. The correlation between the two seemed to match accordingly. So that was kind of good to see that correlated with each other. Starting approximately around the 233rd to 234th day of the year through 256th through 257th day of the year, you can see a rise in activity that selected temporal scale range, almost mirror-like between the plots. That same trend is then followed through the 256 mark. Now, there is a slight decrease in that activity, then it gradually increases simultaneously through the time. Not as closely as the beginning of the specific temporal range, although there is a slight indication that there is an increase as well. This is where we're looking at. Now, for my third comparison, it's the core to wing versus the faculae area. Just in the same selected temporal range, it becomes very clear that there's zero to absolute no correlation amongst the two plots. At the 245th mark, it's almost night and day, showcasing the quarter wing at a much lower activity than comparing it to the faculae, where it has a substantial increase. So this is where I'm talking about here. This is where the faculae has an increase. And this is the quarter wing having that decrease right there. And same goes for the rest of that temporal scale range. Lastly is the fourth set of my plots that are aligned for comparison. It's the quarter wing again versus the filament area. Here it's almost to zero correlation between the two plots. Sadly, this does not support what we were trying to find in our investigation. Now, if we take a much closer look approximately at the same temporal scale range, just like with the comparison against the quarter wing versus the sunspot area, you can clearly see that in the quarter wing, we have that same temporal increase. This time, the filaments have a substantially decrease of filaments, almost to no correlation with that time period. So I mean, like, it's pretty much like opposite from each other. As the quarter wing goes up, filaments goes down, quarter wing goes down, filaments goes up. After the 250th mark, you can see that in the quarter wing, the values become a steady like trend. This is what I'm talking about. I wouldn't really consider it steady trend, but it's gradually increasing slowly compared to the filament area, where it's just like a mixed flux of increase and decrease of these set values here. To summarize my presentation overall, the goal in this research investigation was to see if the filament areas and or the sunspot areas plays a major role at modifying the quarter wing ratio. Now, we do find that the sunspot area modulates the shape of the H alpha the most, while faculae and filaments have a little or negligible effects. These results are relevant to understand chromospheric variability in the solar-like stars. Now, I do want to really emphasize on this, and that during this whole entire research, we were actually only able to focus on one selected temporal scale range. I'm fully aware that more temporal scale ranges are needed to actually support the theory that filaments or sunspots areas play a major role in modifying that quarter wing. For the sake of time, I was only able to acquire and analyze one selected temporal scale range. I do want to note that the first half of my research was spent kind of learning IDL and kind of getting an understanding of the coding language so that I can actually proceed onto this research. And so actually this kind of concludes my research here on understanding the variability of the H alpha line observed at high spectral resolution in the solar atmosphere. I believe that is it. Is there any questions?
All right, very nice.
Thank you.
All right, are there any questions from the audience or from YouTube? I had a couple of questions. A question. So often it looked like when one goes up and another property goes down, does that mean that they are anti-correlated, or you think there's just in that 1 year maybe it was hard to tell whether they are, right? I mean, so right, the two on the top row look like they go up and down together mostly until the end of the year. But yeah, so like right, the two on the left, right, one goes up, one goes down, and then back up. So so do you think that there's enough confidence in the correlation in between these to say whether they are anti-correlated, or just there's no correlation at all?
Well, I mean, you do have to take in a thought that this is only taking out one temporal scale range, and science, one example, is never enough. So,
it's true.
So like, kind of going based off of this one temporal scale range is really trying to reach and say that, the placulae have no correlations with the core to wings, so it's kind of hard to give a answer that they will forever act like this. But
All right. One other way to maybe make the comparison is, instead of plotting them each versus time, you plot one versus the other.
see, that thought actually came into my head this morning, and I actually how we're trying to figure out how I combine all the 4 into one plot, so that way it would be way easier to view the correlation.
Yeah.
And I mean, I got stuck, and I was like, you know what? I can just put all 4 in.
Right.
Ask that question, Marty. Yeah, but yeah.
All right. Are there other questions? Any comments from YouTube?
Thank you guys for all the comments.
No, you did great.
Awesome.
Okay. Well, if there are no more questions, we can close the session for today. I want to let's give all of the speakers a virtual round of applause. Everybody did great. We all stayed on track. We all took our breaks, relaxed. Everybody was refreshed.
It was definitely very rewarding in the end. So.
Yeah. So tomorrow we will start at 9 o'clock again, and I think we have Mountain Time. Sorry, and I think we have one or two fewer talks tomorrow, so it won't be quite as long. It will still be another nice long day, but this is practice for if you go to conferences where you actually have to sit in a room for hours and hours, and then move to another room, and then go get coffee.
Can I just point out that the YouTube link for tomorrow will be different, and I will post it to the schedule page right after we're finished here. So just make sure that you check the schedule page if you want to share the YouTube link with your friends or family or anything like that tomorrow, because it won't be the one that's there today.
And don't forget to fill out the evaluations for all the speakers. If you missed someone earlier but you still remember what their talk was, then you can get those. I think they're pretty helpful, right? Hopefully from the 5-minute talks, those were useful tips. So I think that will happen again. And thanks to all the mentors and visitors and YouTubers who sat in on the talks, and we hope to see you again tomorrow. Any other closing things that I forgot about, Claire?
I don't think so. I think that's everything.
Okay.
Well done, everybody. Congratulations, and good luck for the folks who are going tomorrow. And we will see you bright and early. I'll probably start the Zoom about 8:15 again. So we'll see you tomorrow. That doesn't mean you have to call in at 8:15, but just if you're nervous.